Okay. And
Yes.
okay. Yep.
Okay. All right.
We can start.
Okay. Good morning, everyone, and welcome to the fourth day of week 2 of the CSS. And today we have the pleasure of having Prof. Ilya Sinaski. So Prof. Ilya is an associate professor at UKZN, and he is a C1 rated researcher with his research interests in the area of open quantum systems, quantum optics, and quantum information. And today you'll give us some introduction to machine learning, and I hope you guys engage with him and learn as much as you can. And I'm going to hand over to you now, Prof, and all the best.
Okay, thank you. Welcome, everyone. Yes, as Tutukili mentioned already, my name is Ilya Sinaski, and I'm working at UKZN. And my primary research focus is in the quantum things, but because nowadays everything is using machine learning, I also end up doing a little bit of classical machine learning for the quantum purposes, and a little bit also of quantum machine learning for quantum purposes or classical purposes as well. Okay, so because I'm in the full screen mode, maybe I can ask some of the students here. So if there will be something in the chat which I supposed to see, they can indicate it to me. So there might be a little delay. Okay, so my slides are not my slides, so I need to tell it explicitly. They are based on the lecture slides, from applied machine learning from Penn Engineering, and you're welcome just to Google it and get the full lecture course. But because I'm just going to give you something very short in today and tomorrow, and half of tomorrow essentially, and it will be rather basic introduction, but I would hope to introduce to you some very fundamental and basic concepts. And there will be several tutorials. We'll start with the linear regression, which you're probably sick and tired already of, but you need to start somewhere. And afterwards, we'll go a little bit to the fancier algorithm, and we're going to finish with a little bit of neural networks and a little bit of form of neural network, which is called convolutional neural network tomorrow. Okay, so but mainly it's going to be a set of lectures with a little tutorials, and I will need to decide how we're going to do it. Are we going to do lecture, tutorial, or we're just going to do lecture, tutorial? So if there are some preferences, just tell it in the chat. So now we have a time till 11, and afterwards we have, we can maybe, okay, let's see how it goes, and afterwards we will decide. And for the today, I assume that you all have access to the Python or Colab, and for the tutorials, you will need some standard packages, which you already probably have installed. So you need things like pandas, that I assume you already all have, NumPy, matplotlib. The only thing which you might need on top is scikit-learn. I don't know, have you installed? Okay, I will closer to the break or during the break, I will type the name of the package. You will need to install scikit-learn, but it's a small package. And for tomorrow, you will need a TensorFlow. And I think for the one more graphical thing, we'll need a Seaborn. But this is a scikit-learn and Seaborn are small packages, so it's not a train wreck. But over the evening, you will need to install TensorFlow because for tomorrow, because the TensorFlow is a large package if you don't have it. Because from there, we'll need some primitives to how to build the neural networks. Okay, so let's start. So what is machine learning? And machine learning is kind of like, there are several questions, and kind of like, before we are going to do the introduction and anything, we need to know what are we dealing with. And there are several opinions because, so one of the opinion is this: what is machine learning? Is a learning of any process, but which simply improves performance from experience. So that is one opinion of some person who have been dedicated his life to studying machine learning. There is another opinion. So machine learning gives a computer ability to learn without being explicitly programmed. And this is a very interesting definition or kind of opinion about machine learning, because some people already now talking about machine learning as the programming to zero. means that, when you do in the first week, when you've been taught how to write the programs, you'll talk that you need to formulate a problem that, I don't know, you need to calculate the sum of the numbers, yes? 1 + 1. So you need to write a little program which have enter number A, enter number B, and the program is supposed to spit you out A plus B. So you explicitly program the logic. What machine learning is allow you to do, it allows you to don't program the logic. It allows you to by certain operations, which we are going to talk about just now, you enter a lot of examples and machine figure out logic by itself. So and from this perspective, some people talking about machine learning as the kind of programming 2.0. So you don't program the logic, the logic is learned, or the logic is inferred by your machine learning algorithm. So, and there is even more interesting, or maybe a little bit more complicated, what is machine learning? And machine learning is kind of set of algorithms that improve their performance on certain task with certain experience. And in fact, this definition is from some other angle on machine learning, or this opinion about machine learning. It's from something which is called reinforced learning, or kind of the machine learning where, or kind of it's much more applicable to the notion of the reinforcement learning, which we are going to speak very little about it. But in fact, this is probably one of the most interesting part of the machine learning, because that's machine learning which allows, self-driving cars to drive. That's reinforcement learning is behind the great success of the recent large language model called DeepSeek, or kind of it's not even a large language model, it's a reasoning model, but okay. But we're not going to speak about that, unfortunately, because we just don't have time for that. Okay, so and the typical example where this definition is applicable is, for example, in the typical game playing, because the same reinforcement learning is the key behind the chess games, or kind of the chess algorithms, which are achieved long time ago already by now superhuman performance. I hope everybody knows that the best chess player in the world is no longer human. And if the first one, Deep Blue, was not based on reinforcement learning, the modern chess algorithms are beating up old style algorithms with a very high efficiency. Yeah, so how it's applied here. So the game playing is this triple, well-defined triple of the performance, task, and experience. So T is playing checkers. Yes, so this is our task. P is the win rates against opponents, and the E is the kind of playing games against itself. And that's where the real gem of reinforcement learning is coming in, kind of into the play, and that one can understand why everybody is now will do a lot of this approach, because you really could very easily make the machine play with itself, because you don't need a human, and that means that machine can do it 24 hours without weekends, as long as there is an electricity in your cluster or in your computational system. Machine can learn, and that's essentially what's happening. You can parallelize this process, so you can learn not on the one machine, but you can learn on the multiple machines, and you can find the way how you can put the experience together. But the idea is it's orders of magnitude more efficient. And as I mentioned to you, something like that, but in a little bit much more involved way, was done by the DeepSeek creators. And that's why they managed to train this model to be compatible with the ChatGPTs of this world, but for the very, very small fraction of the cost. Okay, so, but the typical example of machine learning which we are kind of dealing with, or kind of one might need to deal in the real scientific problems, is the problem of the prediction. Yeah, so we have some input data. So for example, in this case, it's arc sea ice as the function of years, and we need to predict where the ice will go. Yeah, kind of what will happen to the arc sea ice coverage all over the world, with as the time is passing. You don't need to do too much of the machine learning just to see that, where the blue, okay, yes, we can see my cursor, good. So where the blue dot is, that's where we're going. But, sometimes you need to be a little bit more precise, and sometimes you need to do a little bit more prediction than just the things which you can do with your eye. Okay, so, and what is the typical algorithms for prediction? The typical structure for prediction is looking like or for any sorts of prediction tasks, you have a lot of data. You kind of apply it to you choose machine learning algorithm, and afterwards you do the training. And we're going to discuss how one can do the training and what are the secrets behind doing effective training and which things you need to keep in mind when you do the training. And afterwards, you have a trained model and you do the new input and it will spit out you some output. Yes, and I will put the slides online. So sorry, I haven't yet done it, but during the break, I will put these slides online, so don't worry. Okay, so there are traditionally, so now people separate even more, but traditionally, as a zero-sum approximation, we can separate 3 types of learning tasks or types of learning, which one can study separately. And this is traditionally what is done. So supervised learning is you provide input and output examples, and your algorithm supposed to learn the logic, how to map inputs to the outputs, and afterwards you provide a new input and it will give you output. And you kind of, if your model is good, your output will be exactly where it's supposed to be. For example, you can use it for predicting something like if it's possible to predict, because there are some things which one cannot predict, which are inherently stochastic, but this is a separate discussion. But it will predict you, and for example, results of the experiment. But the laws which are governing the system are so complicated that you cannot just write a little Newton laws and integrate it, but you can just do it by massive inputs of what is happening to the system, and afterwards you predict some output. So another interesting case, because kind of what is supervised learning, people more or less understand. What is even more interesting, there are methods which are called unsupervised learning, where you just provide the data and you don't know the answers. And what does it do? It finds some structures, hidden structures in the data. And again, there are multiple examples, but and we're going to, in the tutorial, we're going to have examples of unsupervised learning as well, where we just supply some data, and what we're getting out that suddenly we get some, I don't know, clusters of the input data, and one can try to understand what is the logic behind those clusterings. Or you can find what is called the compressed representation of the data. So in the sense, like, you are entering the data, which, have 100 inputs. I don't know, it's some sort of, characteristics which you measure. But in principle, it's not that important. In fact, that all of those 100 characteristics could be represented by 2 or 3 numbers, and afterwards could be reconstructed. So in that case, unsupervised learning is a very nice way how you can get to that compressed representations, and that's also play an important role. Or you can get the most important features, or kind of the most important properties of the system. And the table book examples of those will be something which is called principal component analysis. And there are some other tricks like some nonlinear versions of the principal component analysis, or for example, some special architectures of the neural networks, which are called autoencoders, which can do this job for you. And the last one, which we are really going to do, I'm just going to introduce it and not spend time at all, because it requires a little bit more time and much more practice, is reinforcement learning. And reinforcement learning is you need to define an object, or kind of an agent, so-called agent, which is supposed to learn something. So the agent can do the actions. For example, an example of the agent could be, it could be the game character in the game, which is going to be trained by the machine learning algorithm to play the game. And as we also know, at least those of you who are related to the games like Dota and things like that, they know that the computers now can play better than humans again. And this is done in the training of reinforcement learning. So kind of like the agent is interacting with your environment, and as a result, what you are getting, you're getting some reward or punishment. And as a result, the agent is learning which moves are good and which moves are bad. And and reward and punishment could be, immediate, or it could be long-term. And kind of as a function of that, how much time you will spend to the training of the models, and how long and how difficult it is. Okay, so supervised learning, as I mentioned to you, and it's a little bit of formalization. Okay, so let me check the Slack. Oops. It's in the chat. Okay. Okay, so in this context, does the self-supervised learning fall under the reinforcement learning, or it's completely separate thing? If it's a self-supervised learning, it's probably more related to the supervised learning, but you need to kind of, with just, you know, a little bit of self-modification. What you need to think about is like, it's really a formality and old style division, because now, you know, there is no, like, I mean, there are some supervised learning which use elements of unsupervised learning, and, you know, it's all kind of like fuzzy boundaries. But as the zero-sort approximation, you know, you supply the examples with the answers, it's something which is supervised. You know, you don't supply the answers, you just supply the data, it's unsupervised. And if you do the sequence of interaction and choosing the best strategy of behavior, it's reinforcement learning. But nobody prevents us from building the mergers of those approaches. So this is somewhere in between. But, you know, you don't need to put stuff in the bins, you know. We need to put initially some stuff in the groups, because, you know, we need to start somewhere. I cannot just tell you that, oh, we do whatever we like. Okay, so where we are. Okay, so, and a little bit of formalization. Yes, so we get some point x, y. So in this case, we're in a very fortunate scenario, which usually you are not in. So when you have one input point, one output point, and in this case, obvious solution for this is just, you know, to draw a straight line. And is it obvious or not? We're just going to do just now, when we are going to talk about the how we decide when the model is good enough or not good enough. Okay. So another example of the supervised learning, because this is supervised learning, which is called regression. So it means that we're predicting the value, the real value, which can be in some range, usually, you know, from 0 and 1, or from -1 and 1, but it also could be in the wider range. But, you know, you can always map it. But the idea is that you're predicting continuous value, and this is called regression task. And there is another task which is called classification task. So when you have some input data, but your answers are binary, so yes, no, or class 1, class 2, class 3. So for example, on this example, you know, you have some photographs of something, and in this case is, you know, some medical images, and you need to say, is this photographs of tumors? Is it tumors? Is it will they kill you or not? So this is essentially a binary answer problem. So do you have a bad tumor, or do you have a good tumor, kind of, which will just go away by itself, or it doesn't have a danger? So, and of course, you don't need to have yes, no answers. Yes, no answer is a very typical case, and this is called binary classification problem. But, you know, you can have a more classes. For example, in the tutorial, we're going to do prototypical, you know, MNIST classification. So where you need to recognize handwritten digits, and the handwritten digits could be from 0 to 9. So over there, we're going to have 10 classes. So, and that will be a multi-class classification. But if it's only 2, so if it's yes, no, it's binary. Okay. So typical unsupervised learning is giving you the problem like this. So we have some, again, we're given some input. We don't know the answer. So, and there is not necessarily there is an answer, because there is no problem, but there is just a lot of data. And, you know, as a humans in this two-dimensional case, we could really say that, you know, there are kind of groupings of the points. So we can see that, you know, all the blue points are here. These points are one group, that points are other group, and that points are other group. And sometimes it could be something very useful, because, you know, if it's just your data from experiment, you can try to understand what does it mean. So why these points are together, why these points are together, and why that points are together. And for example, if you're talking about, you know, behavior of, I mean, it could be, again, so you can apply the same logic. For example, in this example, you can take all the photographs of your tumors, and if you apply correct enough unsupervised learning algorithm, you can find out that there will be 2 big clusters. And one cluster will correspond to everybody is healthy, and another cluster will correspond that everybody have a disease, or every photograph will correspond. But you can find it as kind of like hidden structure in the data. Or, for example, physics-based example, it could be, if it's, some data about the ground states of some many-body systems, so that it could be that they belong to the different phases for the physicist in their room, so that, it could be, paramagnetic phase or ferromagnetic phase. And this is very typical example, where the unsupervised learning algorithms are also giving you the nice answers. Okay, so, and where else unsupervised learning is used? And for example, it's used very often in finding, a structure in the social networks. So that's how the Facebook and the X's of this world know what you like and with whom you communicate the most, and how to give you targeted advertisement to you using some unsupervised learning approaches when they just can see the clustering in the data. Another thing, which is kind of a little bit more useful for the science, so that we can identify the types of objects which we see. As I'm going to mention to you, the special types of neural networks, which are called convolutional neural networks, are very good in detecting patterns in the image data, which have some locality property. And for example, in astronomy, the problem is that, you get these surveys of the huge photographs of everything of the sky. It's have zillions of objects, and you just don't know how to put them together. And what unsupervised learning can do, you can apply some other methods to segment it, so that you can say that, okay, this is one object, that is another object, but using unsupervised learning method, you can just say, okay, these are all objects of the one kind, that is all object of the other kind, and so on and so forth, so that you can, for example, separate, okay, this is a photos of the stars of this type, this is a photos of the galaxies of that type, and so on and so forth. Okay, so another kind of like you can use it for the data visualization and for, again, finding the structure in the data. And speaking of finding the structure of the data, recently there was a very interesting kind of like exercise in machine learning, which was done by, I think it was done by PhD or postdoc, who was who's doing zoology, and essentially the person put together all the data about the data about the dinosaurs. And dinosaurs is what everybody is interested in at some stage in their life. Some people do it for their whole life. And we have some historical classification of the dinosaurs. So I don't know, this is a tyrannosaur, this is brontosaur, and things like that, and they belong to the different classes. But that classification, historically, it was built on the as you find fossils, you put them, oh, this belongs to this group, that belongs to that group. Okay, that belongs to somewhere in between, but we need to introduce a new group, and so on. So, and what that students have done, he put it all together and asked to do the classification. So to do the regrouping, and essentially he came up with a much better classification of the dinosaurs. So using exactly, this kind of unsupervised learning ideas, or general classification ideas using the machine learning. Okay, and kind of the last type of learning, but I mean, that will be probably, I think, the only slide which we're going to do with reinforcement learning, because it's, so kind of, what is the reinforcement learning? So we have an agent, which means, have a program which is taking decision about its next steps based on some probability distribution. And you start from, all the ways are equally likely, and afterwards you begin to adjust your probabilities as a function of environment. So the agent is making move, the environment is making response, is giving a feedback, and agent, based on this feedback, is adjusting the corresponding policy, so-called policy of behavior, or kind of probability distribution which guides its behavior. And you can do it on every step if you can make such a decision. But for example, with chess, it's rather difficult. Yes, you don't know whether you will win in the chess just by doing one move. So you need to play the game till the end, or you need to do the sequence of steps to realize, okay, was it a good sequence or not? So, and that's another thing with reinforcement learning, which makes it a little bit difficult in training, and make the training demanding, is that very often the interesting tasks for reinforcement learning are those where the decision whether the strategy or kind of the way of behavior was good or bad is not decided based on the one or two steps, but you need to do many steps, and only afterwards decide, is it good or bad? And if you do many steps, you need to spend a lot of time to the training, and afterwards you decide, oh, it's a wrong move, so now you need to go back quite a few steps and reevaluate. And that takes a lot of time to the training, but as a result, what you're getting, you are getting, you know, autonomously driving cars, which can, okay, we don't have it fully, but we already have it in the certain ways, and you get, you know, the autopilot assistant systems and things like that. Okay, so everyday applications of machine learning. So we know that machine learning is applied in a lot of everyday things, and with many of those things, we don't even know that there is a machine learning behind. For example, we now have much less spam emails than it exists, because, you know, all serious mail providers have a spam filters, which also based on the machine learning and similarities. So that if the text of the email is very similar to the typical spam emails, in that case, you're not going to see that email. Yes, again, self-driving, I don't know, the authentication of you by your face or by your finger, recommended systems. So there are multiple applications. There are, you know, the smart home applications, you know, your circle of friends in the Facebook and so on. So the same things, the machine learning is applied also now, not only in science as the something exotics, it's applied in medicine, and it's very actively applied in medicine. And as I mentioned to you, what is very important to understand that, you know, for the certain classes of applications, such as pattern recognition, certain structures in machine learning are much more efficient out of the box. You know, if you train them well enough, they will be better. So kind of like in case of radiology. So machine learning algorithms already better. They already surpass the level of the average radiologist in making your kind of the saying, do you have a problem or not? And of course, it don't need to replace the person. It needs to give an advice to the person. But the idea is like, you know, the algorithm does not need to go to break. The algorithm does not need to have a lunch. The algorithm is not pissed off because algorithm have a bad client or have an argument with a spouse and that's why, you know, kind of like it's very promising, because, you know, it's going to help. And, you know, there are some examples, but, you know, every day there are more and more examples of when machine learning algorithms are helping to humans to do things better and better. Yes, and the medicine is one of the examples of kind of like no-brainer application, so to say. So because it's like, it will help, it will assist, it will not replace, but it will strongly assist. Okay, even more. So, and this is a very interesting example, yes, AlphaFold, or be more precise, you know, he is saying AlphaFold, but, you know, there is more important version of AlphaFold, which is called AlphaFold 2, because there is a very, very nice problem in chemistry. There was, because not anymore, because this problem is solved. So we all get a lot of proteins inside of us, which are created from sequence of amino acids. And the function of the protein, what does the protein do inside of you and inside of me, it strongly depends on its shape. And it's extremely difficult problem, which was solved by methods of the computational chemistry for the dozens of years. And it's slow, painful, and very expensive computation. And it's not always giving you a good result. And this problem was essentially solved by machine learning, by special class of machine learning algorithms, which are called AlphaFold 2. And I assume that everybody heard about that, because last year, Nobel Prize in Chemistry, or half of the Nobel Prize in Chemistry, was awarded to the people who were the heads of the group, who have trained the AlphaFold and AlphaFold 2. And AlphaFold 2 was exactly the model which managed to do the job of the solvent protein folding. And the performance of the AlphaFold 2 was just a little bit less than the standard which you want from the protein structure for the experimental verification. So it was really far beyond anything which computational chemistry could be providing at any instance. Another examples include, you know, it's used in astrophysics, where you need, again, to do the recognition of the structures, where you need to enhance the resolution. But, you know, this, you can just Google and you'll see a zillion examples of that. Okay, so there are other examples, and this example with the text is extremely outdated, but let's, so that, you know, we can generate images, we can generate text. The image we can, and this is the website which you can trust, which is called This Person Does Not Exist, and it will generate you the images of the people which don't exist. But it just generated using something which is called generative AI, or generative neural networks. It will generate to you images, which are very look like, they look like real images for all practical purposes. And another huge application, which we're all aware of, is the text generation. And of course, I already mentioned the ChatGPTs of this world. And, this is the example. I mean, first of all, this Hugging Face, for those who's interested, is a very nice repository of the all open source large language models, which used for generation of the text. For example, the famous DeepSeek also could be downloaded from there. And this text generation is getting better and better and better. And now it's kind of could be used as a very nice assistance, but students should be careful when using it too much, because there are university policies on usage of the generative AIs. And too much of the usage might be considered by the university as a plagiarism. So you need to use it, you need to learn how to use it, but you need to use it wisely. Okay? So one of the big problems of machine learning, and where the people get very quickly in the trouble with machine learning, is that they have a kind of like when the machine learning works and when machine learning doesn't work, so to say. So, and if you have a data in some domain, yes, kind of we have the data from 1975 to 2015, yeah, and we want to predict something in what it is, 2100 and something, yeah, or something like that, or whatever, but far away. And any model, any machine learning model will very likely fail here. Why? Because here we can see that the trend is rather speaking linear, but we don't know what might happen here. So when you try to predict something, so kind of like if you can train, or if you ask ChatGPT, or ChatGPT, tell me what will happen, I don't know, with Bitcoin in 2050. The probability, of course, the ChatGPT will tell you something, but the probability, and even if you use, some modern version of the ChatGPT, which can Google the internet and things like that, and it will use some chain of reasoning algorithm, it will take the data, it will think, and afterwards, so-called think, and afterwards will spit you the answer. Extremely likely, it will be absolutely wrong. Especially if it's going to predict precise number. I don't know, it will be 255,000 US dollars or something like that. So it will be extremely likely that it's absolutely wrong, because there is so many things which could happen. And how all the machine learning works is that you have your data here, and you assume that in the not too distant future, the stuff will behave the same way. And that is why you can do it. So that, here we see that the stuff is linear, and we can roughly approximate this with linear just a little bit forward in time. And we're very likely to be correct. Or it's non-linear, but we can catch that non-linearity. And how to do that, we're going to discuss just now explicitly. And with the neural networks, you can do it implicitly. So you don't know which non-linearity neural network is catching, but if you supply enough data, it will catch all non-linearities which are in the data. But if based on this data, if based on this data, on the data which we have, one cannot predict what will be here, there will be no machine learning algorithm which can do it. In the same way, in my example with the, for example, Bitcoin price, with the all information which we have now about what's happening in the world, if it's impossible to predict what is going to be with that asset, it means that it will be impossible. And no machine learning algorithm will be able to help you. So, and the best problems are, so when you take the data and your problems are coming from the same domain or kind of next to it. So when you're too far outside, you are not going to get nice answers. Okay, so machine learning for prediction. Yes, as we mentioned, so we have some data, we choose machine learning algorithm, we have trained the algorithm, we get a new input, we get the predicted output. So, and now the question is how to choose this bit. So how to choose the model family, which is a very important question, because, and one of the options one could be that, we take the most kind of rich family of possible solutions. But sometimes it's not a good decision, because the richer the family of the possible options you take, the more difficult it's to train. And as we're going to see just now in a few in the examples, it will tend to something which is called overfitting. So it will describe your training data too well, but it will be very bad in prediction. And we're going to see that just now. Okay, so, and I'm going to demonstrate you some very basic concept of machine learning on the examples of the linear functions because they're most simple. But as we're going to see, and in principle, all the prediction problems, and we're going to see how these tricks are working, are boiling down to the linear functions. All the neural networks, what they're doing for the prediction problems, they are taking your data, which could have, multiple inputs, and it's have very strong nonlinear dependencies. It's identified those nonlinear dependencies in some much larger space. And what does it mean? You will see just now. And separate the data. So class 1, class 2. Such that, so kind of like it's bringing it to some sort of linear thing, because in the very end, you do something like a linear model. And linear models are also very popular in machine learning theory, because that's the only class of models where you can have analytical results. So all the rest are much more difficult, just exactly because of nonlinearity. Okay, so when we're talking about linear models, in the simplest case, what we're talking about, we have some input vector x, and we have the vector of parameter beta. So it means just, and we just find the scalar product of them, or inner product of them, meaning beta 1, beta d, x1, xd. So your input vector have a d numbers. So your every point of your problem is d numbers, and you need just to construct a linear combination, beta 1, beta d, and essentially what is your problem is to choose these numbers from beta 1 to beta d such that you get the best agreement. And what does it mean? We're going to see it just now. So x is called input, also it's called features or covariance, beta called parameters or parameter vector, and y is equal to f beta of x is called label. Label meaning the output or response. Okay. So what is the mathematical formulation of the regression problem, or what is a kind of a little bit rigorous, epsilon rigorous formulation? So we have a input data set, x1, y1, x2, y2. Yes. So where the x is each x, this is x1, xn, is the d values, is this guy. x1 have a d entries, x2 have a d entries, x3 have a d entries, and so on. And yi is just a number usually. Yes, it's just a real number. So if we're talking about regression, so it means that it could be number from 0 and 1, or from -1 and 1. It could be a number in a larger domain, but usually people try to rescale it from -1 and 1 or from 0 and 1. Okay, so, and what we are saying in the task of the linear regression, so what do we want? We want so that, x beta on t or beta on x is approximately y. And what does this approximately mean? And how do we estimate that approximation? We're going to see just now, because that's playing an important role. Okay, so this typical notation, I stands from the elements, j stands from the components of x, and you can think of the xij is the component of the input matrix. Yes, so if you put everybody in the columns, x1 is a column, x2 is a column, and so on. So you get a matrix. So and the goal is to make these betas. So okay, somebody said it. Good. Okay, so let's go back to our covering ice sheet or ice extent. So we have our input data. So now what does it mean? Approximately. So we want to draw a straight line, yes, because it's a linear regression. And we want to, when we say approximately, we want to make sure that, this line is as close to every point on this graph as it's possible. So what does it mean? It means the following. So now what we need to say to you, and we do it with everything. So we need to say kind of like, what does it mean? So that if we have these blue dots, we're going to draw a line which describe, the behavior of these blue dots as the function of input x. So what you want to estimate the average distance. And as we're going to see just now, it's very nice to estimate the distance just by using something like a Pythagorean theorem. So, and to do the, y is the real label, beta x is the predicted label, and there are some reasons why we want to do square. and you will see just now what is the square is, and we're going to introduce the loss function. So, or we're going to introduce how we're going to measure the goodness of the fit. So kind of the distance, the average distance between our linear regression and the input points, yes? And that's what we're going to do. So we're just going to calculate an average of real label minus predicted label. Okay. Okay, so that's give us linear regression problem. You know, we have an input data, we have an input vector, we have answers, and we want to minimize minimums. We want to minimize square error. Okay, so on the fancy language of machine learning, which is a typical, what does it mean? It means that what do we want to do? We want to minimize this function, yeah, over the all possible betas. So if you read any literature on machine learning, and if it's not, you know, just immediately go into the Python code, but it's have an epsilon formula, you're going to see these things, kind of notations like this. And what does notation means? This notation is just meaning very simple thing. So argmin. So we're going to minimize the loss function, yes, our average distance to the answer, over the all possible betas. So we take all possible betas, and in the space of betas, we need to solve optimization problem. We need to minimize this function, okay? And the output is, of course, you know, this set of betas, which is minimizing this function, okay? So, and the very nice intuition why we used minimum squared error loss, because, for example, you know, if we have a perfect situation when our points are on the line, yes, beta is equal to 1, this is the perfect answer. Okay, so in that case, the loss is 0. So if beta is 0,5 and the points are here, the loss will be a little bit larger. And if it's 1/4, the loss will be here. And if it's a little bit larger than 1, the loss will be on this side. So now you can see what will be the logic behind optimizing to find the perfect beta, because the perfect beta will be in the bottom of your nice quadratic function. And, you know, in this case, we can put this quadratic function on the two-dimensional graph, and this is very nice. But in the reality, you know, it will be some multi-dimensional function, and it's not necessary kind of as a result, kind of like, what does it define to you? It's defined to you what is called the loss landscape. So kind of it's defined to you where is your best values are sitting in, which you need to optimize for. And this creates to you a very nice way how you can find these optimal values, because you just need to go down the slope. The problem is, which we are going to see just now, is that when you have more than one minima, and you need to understand how you can find the real minima, because you can have two minima, and you can get stuck in something just called local minima, but that is coming just now. Okay, so yes, in 2D, we're going to have a convex or ball shaped in general, and if we're going to plot like equipotential like surfaces, we're going to get something like this, and the goal is to get to this point, and that will be our optimal beta 1 and beta 2 in two-dimensional case. Okay, so there are alternative approaches to the loss. There is a mean absolute error, which doesn't have square. There is a mean relative error, and very often used in the statistics is R2 score, which is called coefficient of determination, and this is 1 minus mean squared error minus variance. Okay, so now let's recap what we have, and let's try to understand how we can minimize the loss function, and what problems we can get on the way of doing it. So we have family of models, and in this case, it's a linear function. We need to define the loss function. So we need to have model. What are we going to minimize? Yeah. So in case of linear regression, we're going to, this is our model family, and loss function, we're looking like this. And what do we want? We want to go through the all possible values of beta and minimize the loss. Okay. So what does it mean, or kind of like how it could be formalized, and which problem we might face in doing that? can be indicated on the following sequence of the graph. So we have a input data, and we assume that, that there is an unknown function that generalizes Z. So that which means that works very well on this kind of, that can predict whatever is supposed to happen. And this is F star is ideal function. If the perfect answer, which we not necessarily know. And the problem is, the goal is that we need to find approximation of that perfect function, the function which is the answer. And of course, the obvious problem is that, this might be the gray area, might be the space of the functions which you have access to, but the F star could be outside. And your job is to find, the closest function to this function. And what defines this distance is very likely to be on the next slides. Okay, so let's speak about the model families. For example, our data is quadratic function, yeah? And if we're playing our game with a linear regression, we can plot the strain line like this, strain line like this, or strain line like that, and we're not doing good. So the question is, what can we do? What can we do to do things better within the linear regression family? And the answer is, we don't have to, we need, and this is kind of like very crucial idea, which is exactly related to the, that's how the neural networks works. And that's how the all fancy algorithms works for the regression and classification task. So you take your data and you do something with your data. So you modify your data in some way. And that's called, on the fancy language of the machine learning, it's called feature map. So you take your data and you transform your data. In which way? That's a separate story. And that's the beauty of neural networks, that you don't need to think about that. Neural networks can do it for you, because neural networks just go through the wide family of possible feature maps and select the best one. And that's why neural networks are so successful. Okay, but how to work in the other cases? And the idea is that now you're playing linear regression, not with data X, but with its transformed data, phi of X. And of course, all the rest is the same. But now you're just playing with the transform. You take your data, you transform it, and you do linear regression. And in our little example with the squares, it's very simple, yeah? Because again, we know the answer so that we can play the game nicely. So our feature map will be, we take in every point of our data, and we add into our data the square of the input data. And in that case, our model family, which is still linear regression, is in fact a quadratic function. But you can imagine that, this could be any function, as if even a function which, which is very difficult to put it on the single slide. If it's a neural network with hundreds of layers, it's just doing some nonlinear transformation with your input x1, x2, x3, and so on, such that afterwards the data is so-called linearly separable. Okay, and of course, in that case, we know the solution. We can find that the beta 1 needs to be very small and beta 2 needs to be equal to 1. Yes, so we're getting like a perfect fit. Okay, so using this idea of the feature maps, we can really nicely kind of put on top of the linear regression, nonlinear transformation, which can explain our data. And obviously, the nice idea is to say, okay, now we can do the cube, we can do the power 4, and so on. Yes, but there will be some issues which we are going to discuss it. Yes, so feature maps are very often used. Yes, if you have an input and phi of X is features. So, and very often people will say input and the features interchangeably. That's why, because it's usually nothing is linear by definition, and you need to play some feature maps games always. Okay, so you can have a polynomial feature maps. Yeah, so quadratic features are very common. So you can have a polynomial feature maps. You can add a free term or intercept term into the linear regression. You could have some other kind of non-real numbers inputs. For example, so you can feature map will give you 0, 1 here if the answer is good, and 1 here in that place if the answer is bad, and so on. So kind of like you can use the feature maps to do various things of the, even in the data encoding by itself. And as a result, so all of that is reducing back to the linear regression by, so you choose the feature map, you apply it to your data, and afterwards you do a linear regression problem, but not with the input data, but with the feature mapped data or transformed data. Okay? So, and now there is a very important question of the very important thing. Why not, if we see that, it looks like, that the more features we include, the better we get. And the answer is not always. So, for example, why not to throw immediately, the high-level polynomial? For example, we get a bunch of points, we train, and it looks like this. And this is a polynomial of the order. What is the minimal order of this polynomial? It could be higher, but what is the minimal order of this polynomial? No. What's happening in the Slack? Okay, so I get the correct answer in the Slack. No, degree n is not correct. No, what is the minimal degree? What is the minimal n? No, it's 5. And there is a correct answer. It's 5. Why? Because you have a, if you just take this graph and shift it down, you could have a 5 zeros. It could be 7. It could not be 6, because if we assume that these are going, so it's have to be odd, but it could be 5, it could be 7, and so on. But minimal is 5, yes, because we have a 5. Yes, and the 4 will be both up or both down. Okay. So the polynomial of the order 5, and why it could be not a good idea, because we don't know what are the new points. And we're fitting so well existing points. So when we add in new points, the red ones, they're fitted horribly. Yeah. And this is very important trade-off. And the machine learning and kind of, it's all about the trade-offs. You need to give to the model enough freedom to capture the data, but not too much. Because if you give too much freedom, as in this example, what happens? You are describing too well training data, but in that case, there is a chance that you are horrible at describing new data. And in fact, the much better model to describe the blue points was just a line, or just a linear regression without any polynomial features. And now there is a very important question: how to decide? Because you have the same question in the neural networks, and in the tutorial we're going to plot the corresponding graphs to see how to decide, when it's enough. Okay, so, and how to decide? What do? You do the first thing. You need to, because you don't have, that data with the red dots. You don't have it usually by default, so you need to create it. And how you create it? You take part of your training data. So you take a training and testing data. So you take your training data. So you take your old data and you split the bit. And there are different splits, and there are different philosophies on the splits. The typical splits are 80-20. Sometimes people do 2/3, 1/3, but it depends also on how much data you have, and you need to do experiments and see how it goes. Okay, so you take all your data, you split to the training data, and you take to the test data. And for the test data, you don't use it in training at all. So you use it only for testing, meaning that you do whatever you like with the blue data. And when you're convinced that you have done everything right with the blue data, you plug in the red data and estimate the error. Okay? So, and there are typical words which people are saying. One is called overfitting and another is called underfitting. So what is overfitting? Overfitting is when you are fitting perfectly or very well training data, but you are very bad in the test data. So it means that your model have too many options. And what you need to decrease the number of options of the model. And underfitting is when your model is bad in describing training data, and it's also bad in describing the test data, and it's called underfitting. So it means that the number of options of the model, so kind of like where the model could extra kind of, or it's called formally, it's called capacity, and I think it's coming on one of the next slides. So the capacity model is just not enough to capture the data, and that's kind of like, this is two opposite cases. And the kind of the correct answer, so to say, or the answer which will give you a good description, is somewhere in between. So you always start from the underfitting, and you improve you give to the model more and more options, model work better and better. But on some stage, what will happen, as we are going to see, that your test accuracy, or kind of the test on or accuracy on the unseen data, will begin to raise. And it's mean that, okay, now you need to go back to the point where the test accuracy and the training accuracy will both going down. And that's, you will be in exactly in a good enough spot. Okay. So, and there are, questions why overfitting happens, and overfitting happening because of the noise in the data, and kind of like, there is always a noise in the data. Yes. So kind of like, because that's a real data. So because sometimes there is a problems with the labels, sometimes there is a problems with the features, but sometimes, we also don't know the capacity of the model. Okay, so what is a generic algorithm? We take a given data, we split it to the training data and to the test data, and we solve the problem. We run the linear regression or whatever on the training data. So we obtain the betas by minimizing the loss, and afterwards we're evaluating the loss on the test data. So betas are produced from the training data, and afterwards we use test data to calculate what is the loss. And we can, yes, again, loss train is small, test train is large, we are overfitting. Loss train is large, loss train and loss test are large both, we are underfitting. Okay, so now how we need to do it? We need to choose the right model family. And when people are talking about the model families, they usually speak about what is called the capacity of the model, or and the capacity of the model, the kind of intuitive definition is, how much, what is the complexity which model can pick it up. The high capacity is the model which can catch a lot of complexity, but this usually corresponds to you will likely overfit, and it says that the model family have a high variance. And if it's have a low capacity, so it's tend to underfit, so the model family have a high bias. And for the linear regression, the capacity corresponds to the number of features in your feature vector. And very often, exactly the same thing. It's exactly overfitting against underfitting, but in some other textbooks or in other ways of doing it, it will be called the trade-off, not between the overfitting vs underfitting. It could be called bias variance trade-off. So that you need to choose between the model capacity. Is it very expressive? So can it catch a lot of complexity? So if it can capture too much complexity, you are very likely to overfit. So you need to decrease the complexity of the model slowly, or you start from the high bias, so very model which is underfitting, and increasing complexity step by step. Okay. So, and this is a very important graph which you are going to see in all of kind of the simple machine learning models, because in more complicated models, you will get some modification of this graph. So you have your loss function, and you have a capacity. And in case of linear models, so we can think about polynomial order of polynomial which we are fitting in. So the blue is training loss. And as we increase the powers of the polynomial, as we can see, we'll get better and better agreement with the training data, and our training loss will go down until it's reached 0. But what will happen to the test loss if we do things right? The test loss will also start to go down, and afterwards it will plateau, or kind of like it's unclear what's happening, but afterwards it begin to grow. So what do you need to do as a machine learning engineer? Is that instant? Do we need to split the data? First, I will upload the nodes just now during the break, which we are going to have in half an hour. Yes, and the question also, do we need to split into the training, testing, and validation? Yeah, we're coming to that because we need to split into the test, training, and validation when we'll have more stuff to optimize. Because just training and testing is not enough. But that is coming, don't worry. That's all questions, yeah. There is can the quadratic function be used to plot the expected magnetic curve of something which I don't know what it is? I'm sorry. You can use any function if it works. Okay, so I hope I answer everything. Okay, so, and in case of neural networks, we're going to see exactly these graphs, which are going to tell us where we need to stop in the training of our neural networks. And so while we're here, so as we increase the capacity of the model, or kind of, if we're thinking about linear models, as we increase the degree of our polynomial, and the both test and the training loss are decreasing, it means that we're doing fine. We need to increase the power. But in the moment when the test loss begin to raise up, it means that, okay, we have done enough and we should stop. And you should just go back and see what parameters of the training model were in this area. And that should be your area where you should use it for prediction and for the generalization, applying your model to the real data. Okay, so, and this is, again, that is called, sometimes you can call it underfitting, overfitting trade-off, or sometimes it's also called bias variance trade-off, but it's mean exactly the same thing. So for linear regression, this is the capacity correspond to the dimension D, and yes, and there are some rule of thumbs when the stuff is working, and that's another thing about machine learning. There is no definitive rules. Like there is a lot of rule of thumb, kind of like in the training of this type of models, usually this works, or in the training of that type of models, usually that works, because you're going to kind of like, you need to choose, what kind of how long you need to train, for how many iterations, how you need to split your data. And, for the different types of models, and also for the different types of data, you just do it by training. But, if you work with a similar data, for example, if some of you decide that you want to do, I don't know, some large language model training of, I don't know, not African indigenous languages, which is probably is not done by Google, and it's only a problem of the interest for the African continent, objectively speaking, because that's their heritage. That's over there. You need to take some experimental observations which people get from the training large language model on other languages, and try to see how it will work in some, for example, African indigenous languages and so on. But there is no kind of the hard rules, and that's what you're going to see in a lot of, if you are going to read the literature on the machine learning, or you are going to go to Stack Overflow to see for the answers, what's happening with the stuff, what you're going to see very often, that there are just, rules of thumb. So people do the experiment and they've seen that this works. Okay, so it means that you need to try it as the initial point and see how it works. Okay, so how you can visualize that bias variance trade-off with our gray circle. So our ideal function, f star, is here. The model family, so kind of the possible models which were here. So the total loss is the distance from our function which we're training to that function. But what is correspond to the bias and variance is exactly the kind of the distance to the boundary, kind of the distance between what we train and what we ideally could achieve is this one. This is your variance, and this distance is bias. So this is just another kind of way, or that's a way how we can characterize the errors. Yeah, so kind of like when we're in an overfitting scenario, it means that we're somewhere here. So our model is far away from that kind of the boundary model. but this distance is small. So this is overfitting scenario. And this is underfitting scenario. So it means that our model family is just too small model family. So kind of like we are almost close to the best result which we can get within our model family, but it's still far away from kind of the true answer or kind of like ideal answer, whatever that means. Okay. So in an ideal, you want to be kind of like some kind of like in a perfect case, you want to be something like that. So you want to be not too far from the boundary and not too far from the ideal, kind of the F star.
Mm.
Yes, we're going to talk about the neural networks tomorrow. What is the difference between the test and validation data? That is coming just now. And can you please explain the bias variance trade-off again for those models? Bias variance trade-off is the best understand where it was here. So when your model, I mean, just think about, when you're talking about the linear models or linear regression, and this linear regression with the features when you can have a quadratic, so you can you see for the distance, how good you can do the linear regression for the kind of quadratic function, cubic function, fourth order function, and so on. So as you increase the power of polynomial, because if we're talking about in the plane, obviously the higher polynomial you take, just because of the Taylor expansion, the better will be your fit. Yeah. So in principle, you would think that you can get a perfect fit by taking as many powers as you have. But the problem is that without taking into account that your new data is not necessarily follows your perfect fit of your training data. And you just need to be good enough. So you don't need to be perfect. You need to be good enough. And that is called high variance or overfitting. So if your model have too many parameters and you perfectly fit the data, you perfectly fit the training data, it's very likely that you're going to be quite bad on the test data. And so this is called, the situation is called high variance. So high bias means that your model is just not good enough, because we're dealing here with the quadratic data, yes, which is obviously coming from the quadratic equation, but we're trying to fit it with a linear function. And there is no way when the linear function is going to fit nicely quadratic. So it might be doing okay here, but next point will be here, next point will be higher. So it's again out. So what do we need to do? And this situation is called high bias, and kind of like, what is the solution to this conundrum? So between the low capacity of the model and the high capacity of the model, that you need to just find some point somewhere in between, when the capacity is good enough, so high enough to capture the complexity of the data, but not high enough to be bad on the test data. So, and this is a trade-off. So you can choose between the high variance or high bias. And you need to choose a path somewhere in between. And as I mentioned, practically you do it like this. So you split your data to the test and training. So in case of linear functions, what you can try to do is just you try to fit it with a linear function. You calculate the training loss, test loss. Afterwards, quadratic function, test loss, training loss. Cubic function, test loss, training loss, and so on. You do it step by step. And what you're going to see that on some stage, your training loss is always going to decrease if you do enough training, or kind of like very likely to decrease. But what happening to the test loss would be a very good indicator where you are on your trade-off, and you want to be in the point where you stop decreasing and you're about to increase. So that will be your perfect point where you need to choose your stoppage. Okay. Okay, so let's go. Okay, so now we're coming to the problems of why we need test, training, and validation set, why we need to cut more. And this is related to the very simple fact. And very often what people will do, you need to do what is called regularization. And what is the very simple logic of it? So kind of like very often you have your loss function, but you want to add something else to your loss function. Why you want to do it? And the reason is very simple. So sometimes, because as we are going to see, what will be the way to find these values of beta will be kind of using some numerical technique. And it could be that, you are walking into the loss landscape, because it's not always a nice, one ball where you go to the minimum of the ball. For example, you can just type now in Google, neural network energy or loss landscape. And you'll see that it's a very hilly surface with a multiple local minima and with some deeps and kind of like with the deeper deeps and your global minimum could be somewhere in the corner, and it could be very deep. And that's where you want to go. But if you're stuck in one of the local minima, there will be no way how numerically you can get out of that point. And in order to do that, what you need to try to do, you need to try to say that, okay, I'm looking for all possible values of beta, but I don't want that some group of the values of beta or values of your parameters are favored by the algorithm, or they should be favored only if it is necessary, if it's true performance of the model, if it's not local minima. And how you can do it? You can do it by just adding simply the sum of all terms. So, and what does it do? It's going to increase our loss function if suddenly one parameter begin to really become very large and all the rest parameters are very small. So in that case, it's going to be this term to be very large, and it's going to correspond to the very large loss function. So what you want a little bit everywhere, and it's get some values only where you want it to be. So this is called regularization. And this is one of the forms of the regularization, because this is what is called L2 regularization, because this is just, kind of beta 1 squared plus beta 2 squared, beta 3 squared, and so on, because this is just something just called L2 norm of that vector, but, it just sum of the squares. And what does it, kind of which problem does it present to us? Because now we have some also parameter lambda, which is telling us, how badly we want to punish our loss function for this kind of, for the different values of beta. And that's that thing we need to also to kind of optimize. We need to find the optimal value of the beta. So, and what is the interpretation of all of that? The interpretation is, or intuition behind the regularization. So first of all, it's encouraging simpler functions. When the lambda is very large, betas become very small. And kind of people use the lambda to tune exactly this bias variance trade-off. And how you can graphically imagine it. So our original loss was looking something like this. Yes, so kind of like our kind of our squares here. So beta squares correspond to this. So now our total loss, so our landscape, will look such that, so what we want to do, we want to be somewhere. So if we're here, it means that, we're dominated by the regularization term. If we're here, we're dominated by the loss term. But the kind of the good answer, which correspond to the good enough capacity of the model, will be somewhere in between, where the loss from this side and the loss from this side are balancing each other in some way. So, and now that's create to us some challenges, how we're going, what will be the procedure of how to find this lambda, and how to, so now we not only need to find beta, but we also need to find lambda. And the question is how to do that. And so yeah, we can do also intercept terms. Okay, so let's skip it. Okay. And there is one more thing which we're talking about. Yes, which I mentioned that that the regression is from 0 to 1 or from -1 to 1 problem is usually, so what you want when you do all of these games, in order to make it fair kind of judgment, what you need to do, you need to bring features or all the input values to so that they're comparable to each other. Essentially, that's what you want, because if you're along the one axis, your x is large, along the other axis, kind of if all x1s are large and all x2s are small, what you will get some imbalance between the betas to compensate for that. But it becomes very difficult to deal with it. So what you usually do, and there are several approaches or several philosophies which you can choose. So you standardize the data. So what you can do, first of all, you can One approach is you can bring it to the being Gaussian normal variable. So you take your input data, you calculate the mean and you calculate the mean and deviation, and you subtract the mean from your input data and divide by the square root of deviation. So your input data are as if they're coming from the normal distribution with a variance of 1. So this is one approach. The other approach is that you can do min-max scaling. So you can take all your input data and scale it between so out of your minimum and maximum value to be from, I don't know, -1 and 1, or from 0 and 1. So you just rescale it so that all the inputs of all the vectors are comparable to each other. So in that case, we will get comparable betas, and we can give them a fair judgment or fair estimation. Okay, so yes, and you see that's, but kind of like this is a standardly done, so we don't need to think about that, because this is a standard part of the most machine learning packages where we don't need to do it manually, and it could be done automatically for us. But the logic is the same. So you calculate the mean of your input data, so you calculate the variance. Yeah. So what you do, you just normalize your data. You subtract the mean and divide by variance. Okay, so now what do we need to do with our loss plus regularization strategy? So we need to find the way of optimizing it. So in lambda, in this case, is called hyperparameter, because it's not a parameter of the model, it's a parameter which parameterizes the family of models, because the different lambdas will correspond to the different betas. So, and very often you have this, you say, oh, hyperparameter optimization. So it means that it's optimization of the parameters which parameterize the families of models. Because for each lambda, so if lambda is equal to 1, you have a 1 kind of options of betas. For the lambda is equal to 2, you have a different. For the lambda is equal to 0,1, you have another type of parameterization. Okay, so, and that's where we need validation. So that is the answer for the question which was in the chat. So we need to choose the best possible lambdas. So how do we do it? So that we can compare the different families, feature maps, and so on. So we take all our input data and we split it into the training data, validation data, and test data. So, and very typical way of doing it, if we're talking about the training, validation, and test, is 60-20-20. But again, you can do, it's optional as a function how much data you have. So if you have a lot of data and you want to go most into the training, you can do 80-10-10, or 70-15-15. But the typical thing is, and I think in many packages is the default setting, it's 60-20-20. But again, you see, it's this standard word which you're going to see. It's a rule of thumb. People have done experiments and they've seen that it works the most the way. But there is no hard proof that this is the best split. Okay, so what do you do? So we split all the data into the training, validation, and test. And now what do we're going to do the certain number of experiments. And in this number of experiments, what we're going to do, we are going to do the training. And for the given value of lambda, we are going to use the validation data to estimate the loss. Yes, and we don't touch the test data. So we use the blue data for the training for the given lambda, and purple we use to estimate the loss with that given lambda. And we do it for the multiple lambdas. And afterwards, out of that family of multiple lambdas, we choose that one which have a minimal loss, and we do the testing. And that's the result which we report. Okay? Okay, so now we're coming even to the more fancy part. So what you can do, because what sometimes is happening, because now you see we begin to slice the data quite seriously, and one of the problems could be so that by some random reshuffling of the items in the data, what could happen is that you are getting a good result. And I think now we'll go back to the gray areas to describe what kind of errors do we have. And in order to make sure that we're evaluating the performance of the model itself, what you wanted to do, you want to reshuffle this order of the things. And this is called cross-validation. So for example, threefold cross-validation, what you do, you keep the same data for the test data and you don't touch it. But you take your training data and validation data to be this. So you use blue for training, purple for the checking the value or find the optimal value of hyperparameter lambda. Yeah. Afterwards, you split it differently. So you take your training to be here, and the validation to be this one. And you get what will be the best lambda in this case. And you do the same, for example, if it's a threefold, it means that you split it into three folds, and you check the value of the lambda from here. And if you're really estimating the performance of the model, and you make which is independent of data, what you will see that the lambdas which are performing good for all these three cases should be comparable to each other. They might be not perfectly identical values, if it's a continuous parameter, but it should be close enough. I don't know, it could be 0,1, 0,11, 0,09, for example. Okay, in that case, it seems like 0,1 lambda is good enough. And you can do the estimate and of course, in your reporting of these values or reporting of the test, you can use it as the average, and you can calculate the variance of your performance on the test data. Can the validation be explained again? Okay, so I mentioned to you that I told you already that when we're dealing with a loss function, we know, or kind of we pretend to know, it's coming, how to find the best values of beta. But I mentioned to you that it's a very healthy situation to introduce an extra term in your loss so that we can punish the certain values of beta which will tend to in the wrong direction. And this is called regularization. And now we need to choose this lambda. And the thing is that this lambda is defining to us the families of possible betas. Because if this lambda is very large, it's going to favor very small beta. If this lambda is very small, it's going to favor the kind of other values of beta. And which lambda should we take? We have no idea. And the only way to find which lambdas should we take is to try to see what is the performance of the model for certain values of lambda. And so how we do it? We do it like this. So we take our data, we split it into the 3 bits, 60, 20, 20. So we use the blue one for train. So we pick a value of lambda. For example, you say, I could consider lambdas from 0,1 to 1. Yeah. So with a split 10, so 0,1, 0,2, 0,3, 0,4 until up to 1. Good. So we have 10 possible values of lambda. We put value of lambda 0,1. We train the model with that loss function. And we use this validation data to get loss with the 0,1. Yeah. So now what we do, we train the model again from the scratch with the lambda 0,2, and we get the loss with the 0,2. And we do it here back and forth 10 times for all 10 values of lambda. But we don't we don't do anything with the test data for now. Yes, and what do we do afterwards? So after we get the 10 values of the loss functions for the different 10 values of lambda, we choose the minimum. Yes, and that's what we're going to apply into the test data, and that's what we're going to report in our result. Otherwise, if we don't do this split into the 3 pieces, we don't know where what is the performance on the real unseen data. I hope that answered that question. What is the difference between validation algorithms and I don't understand the question. There is a big difference between validation algorithms and the bias variance trade-off. Bias variance trade-off is just a way how you to find optimal capacity. So do we fix the beta values when we learn lambda and we fix the lambda value and we learn betas which correspond to this lambda. And we use the validation data to get loss for the given value of lambda. Okay. Okay, so this this is the same, but in the words, so that when the z is small, we can split into the 3 steps and things like that. So what could be done? So, but yes, I mean, the main problem is data. You want as much data as you like, because, you know, 3-fold validation is very small fold, because usually you go for the 5 or 10-fold cross validation. So you split it into the 5 or 10 folds. But for that, you need to have enough data. And that is a separate problem. And I think, yeah. Just get over this one again. Yeah. Okay. So the idea is like, you know, what is this 3-fold cross validation? Is it's a very simple idea. Just imagine that, you know, our input data by some random choice is not, you know, purely random, but, you know, it's like 1, 1, 1, 1, 1, 0, 0, 0, 0. Yeah. So, and if we try to predict, you know, and if we use for training sequence 1, 1, 1, 1, 1, any algorithm will tell you what is the next value. Next value is 1. Yeah. So, and in order to get, you know, that, you know, next value could be 0, what you need to do, you need to kind of use the different parts of your input data for training. And that's what you do here. So you take your training data and validation data, and you kind of, you cut off the test data and you put it aside. And it's a separate story how to cut off the test data. Because in order to, ideally what you wanted to do, you wanted to plot the distribution of your, kind of plot the values of your training data and test data, and they should look similar. Because if they look very different, it's very unlikely that your machine learning algorithm will work. But okay, let's say that we've done it. So we cut test data, and luckily again, there are good enough functions in the packages which are built in, which can do it for us. We can say test split and make sure that the distributions are the same if you need it, if your task is like that. But afterwards, what you need to do, you need to take your training data and split it into the true training and validation to find these optimal values of hyperparameters. And because in this case, you can just by random choice, you can have, you know, to make sure that, you know, you're evaluating the performance of the model, because what you want the performance of the model only. If you have a performance of the model and data, it's not good, because, you know, because it might be that your algorithm is working well just because of random distribution in the data. But it means that, you know, if you try to predict the data which not satisfy this random distribution, you're going to do bad. So, and you want your model to work well, and that's why you use the different parts of for the pure training. So you split it. And again, you don't need to split it. There is a function k-fold cross-validation, number fold 3, and you will get it automatically in, for example, in scikit-learn. And you do absolutely the same thing, but what you expect to see, that the results of these splits are comparable. So that's what you wanted to see, that, you know, that the loss value of the loss function here, and here are comparable. So it means that, you know, you're doing good enough for the given of the value of the parameters and hyperparameters. But if they are in all spots, it means that something is off, and you need to maybe do the kind of better capacity of the model and things like that. So you need to do extra tricks.
From here now we have training. We have ZT training.
Mm-hmm. Yes. No, but you see, it's here. Z2 is here. So we just called, you know, Z1. So this is fold number 1, fold number 2, and fold number 3. So it's just, you know, it's just a formality. So kind of you just use the different parts for the kind of for the full training round. Okay. So I think we need to take a break, yeah? And afterwards, and I can upload so let me see if there are any more questions in the chat. Is lambda designed to be always 0,1? No. Lambda is whatever you want, but you just try and see what works. I just give an example. So from 0,1 to 1. But, you know, it depends on the what is happening. Okay, so please tell me where optimization comes in between validation and test data. Optimization will comes in the way how you need to choose betas. You know, for linear regression, and you probably have seen it, and I will mention it, it is, you can write a formula, but there are reasons why you don't want to use that formula. I'm going to mention it. But optimization will come exactly in choosing of the betas. If model that do not consider validation, but only train and test and cannot be considered reliable, no, or not very reliable, you know. And again, if you have a hyperparameters and you always want to have a hyperparameters, you need to have a validation.
I Prof, we can
Yeah.
take a break. We can take a break.
Okay. Now I'm just trying to answer the questions in the chat.
Okay, thank you.
Okay, and so the last thing which I will answer is about certainty. There is no certainty in machine learning. You try and you hope, and you get an evidence that stuff is working, but there is no certainty. Sorry. Yes, yeah. But I'm just answering the questions in the chat because yes, I also have nothing against T. Where is? Where is my? Okay. Nice.
Ilya, thank you very much. If you can hear me, thank you so much. Okay, guys, we're breaking for tea now. We'll see you soon. Thank you.
Okay. Hi, sorry, is Benjamin around? Or can somebody help me with Canvas? Because I could not understand how to add files to it. I uploaded them in, but how to add them to the course? Ah, okay, good. Now I see it. I think I'm good.
Hi, Prof. I think you can start.
I'm just fighting with files in Canvas. Just give me a minute. I'm trying to make the file visible, but it's by whatever reason it's not make it visible in Canvas. I don't know what's going on. Can somebody who have admin rights in Canvas make it visible? Okay, ask Benjamin to help us and where is my
Hi, Ilya. Sorry, you uploaded a CSV and a Jupyter notebook, right?
Yes, and Jupyter Notebook is status is only available to students with links. How can we make it visible?
I think I checked with one of the students' account and it's okay. People can download it and
People can download it. Okay, good.
yeah,
So
yeah. Okay.
because I'm trying to change the permissions, but it doesn't change it. Okay.
No, people can download both CSV and the Jupyter notebook, so it's fine.
Okay, good. Let's go in that case back to business. So let's quickly wrap up the training procedure. So where we were. Okay. Okay, so we stopped here. So let me go to the slideshow. Okay. And now share. And afterwards, we can do some very simple example so that the people can do a little bit of Python and debrief to some space. Okay. So that's where we finished to you before the, so you can hear me, yes? All good. Okay, good. Okay, so we finished somewhere here with a discussion about the threefold cross-validation. Yeah, and I mentioned to you so that, we have that L2 regularization loss, but there is also L1 regularization loss. So there are different ways how you can choose how to, so to say, punish the values in your model so that the model that you get the best possible solutions. And another option is this, what is called L1 regularization, where you just sum absolute values. And the problem with L1 and the similar things which are related to the absolute value is that, when we are going to do numerical procedures, we will need to take a derivative or estimate the derivative of thing. And the problem with the absolute value, for those of you who remember a little bit of mathematics, sorry, and I also think that, yeah, that it's a little bit ill-behaved in zero, so it's non-differentiable. So, but it can make it, it can make to work. But there are some simple mathematical problems which people need to overcome, and the kind of the intuition behind that, the kind of the absolute value in 2 dimensions will look like this. So, but again, the intuition is the same, so that you want to have a nice balance between this part and that part, and you want to find some sort of the point exactly in between. And again, absolutely the same story. And in fact, you can use both L1 and L2. And that will be not in tutorial, which we are going to do just now, which is already in the canvas, but in the next tutorial. Again, yes, kind of like it's all the same thing, so that we can try to select features or to do the optimal choices. We need to, in minimizing loss, achieve whatever we want to achieve. Yeah. So, and now, for those of you who are not really mathematically inclined, you can just close your eyes for a second, because it will be an epsilon part of mathematics, but which is just telling you that, in principle, and why a lot of people do a lot of linear regression based things, that you can in principle write and solve everything. But there are serious reasons why you don't want to do it in practice. First of all, because it's only work for the linear models. And the second most important thing is that you cannot always do it. That's a second important thing. So, but for those of you who are a little bit mathematically inclined and who want to think that the machine learning is not only thumb rules, there's a little bit more harder science, that's a bit about which is related to the linear regression. So if we imagine that the action of all our n training points, we're applying our linear model. So it means that it's a beta on X. It means that it will look something like this. And as I mentioned to you, those X's we can imagine as, in this case, we need to write them as, this is the input point 1, input as the rows, input row 1, row 2, row n, and the D is the number of features, so number of input points. Yes, in the two-dimensional cases we have, it will be D is equal to 2 and so on. Betas are here, and this could be mathematically written as a rectangular matrix, not a square matrix, X multiplied by beta from that side. Okay, so, and the task of linear regression is looking like this, and we need to optimize the betas. And even more, we can rewrite the loss, but let me just go very quickly in this vector notation, and we could formally, to find what is the minimum, we can formally differentiate the function. So we can find the gradient and put the gradient to 0, and formally it is solvable. So the gradient of the loss will look something like this, where the xt is the input data, y is the vector of the labels, and the beta the thing which we need to find. And afterwards we need to solve linear equation, which is looking like this. Yes, and what do you need to do for that? You just need to invert this matrix, and this matrix is square because it's X transposed on X. So, and in principle it's possible, and this is a closed form solution for the linear regression. But as I mentioned to you, this is not always a good choice. First of all, because it works only for the linear models. Yeah. Secondly, because very often it's a very difficult task to find the inverse of a very large matrix, because it strongly depends on the properties of the matrix. And the nice example is here. If you have a matrix with the values 1, 2, 1, 2, you can try to invert it, but it will never happen. Yeah, because the determinant of this matrix is 0, and this matrix is officially uninvertible. But still, one can play the minimization game. Yeah. So the shortcoming of the closed form solution, or why we don't want, in general, use kind of closed form solutions. Yes, because computing of the inverse could be challenging. It also scales unfavorably. So if you have a very large system, the inverse is scaling as the size of the matrix cube. So if you have, a 10,000 features, so it will require quite a bit of operations, which you are going to run out of memory. And even if it all works, the problem is that, if you have a matrix of the similar kind, but in the very large dimensions, numerically, this procedure could be very, very difficult to do. So what can we do in return? We can do something which is called gradient descent. And this is a very important bit in the sense of that's how all models are trained. Because in the doing gradient descent, we don't care. Are we dealing with linear models or are we dealing with nonlinear models? We are doing always gradient descent. We are doing it with some options, some subsamples, and so on, but we're always doing gradient descent. Okay? So what do we need to do? So we need to choose some random values of betas. And as we've seen in the example where we have some, so what do we need to do? We need to go down the hill. So how we can go down the hill? Very easy. Yes, because the gradient for those again who of us remembers a little bit of calculus, is indicating gradient of function, the direction where the function grows. So, but we don't need to go up the hill. If we do the minus gradient, we go down the hill. So and this is simple update rule. So if we just take some set of random values of the betas, and what do we need to do? We just need to go, we need to do multiple iterations of the small change in the direction opposite to the maximum growth of the function. And of course, we get one more hyperparameter, which is called learning rate. It's how fast we go down the hill. And there are reasons why you want to play with this parameter, which I'm going to tell you just now. But this is important because you will need to do the learning rate. You need to choose learning rate. Also in training, I don't know, neural networks and things like that. And over there, it's even more important. And that's why, you know, there are different ways so that you can choose the small learning rate, or you can choose the big learning rate, or you can choose the learning rate, which is even not constant. So as a function of the training of your model, you can start first with the larger learning rate, but not too large. And afterwards, slowly decrease it. And why you wanted to do, I think there should be an image right here. So what is the intuition behind the gradient descent? The intuition is that, you know, that the loss landscape, or this landscape of this, our loss function, could be hilly, it could have a multiple hills. And if we go down the opposite direction of the maximum growth, we're going to go to some minimum point. Okay, so we can go there, or we can go here. And ideally, we want to end up in the lowest point on our kind of landscape. Okay, for the linear functions, the loss is convex, so it means it's a ball without extra extra minima. So there is no local minima, there will be only global minima. It's so good. But in the moment when you go to a little bit more complicated models, and as I mentioned to you, I don't know, have anybody tried to Google just loss landscape neural network? Just Google it, and you're going to see that it's a very, very kind of fuzzy thing with a multiple local minima, with the dips and things like that. And from there, you need to find the global minima. And, you know, it's also visualized in the kind of like in the 3 dimensions. But in fact, there are more dimensions, because the number of dimensions is the number of your free parameters, which you're trying to minimize. And, you know, this is extremely non-trivial task. And, you know, all the thumb rules, which I mentioned, are coming exactly from the fact that, you know, that you need to do something which is supposed to work somehow. But, you know, the only way of doing it is doing numerical experiments and learning from them. Okay, so what is the logic behind learning rate? Because you will need to choose the learning rate. So, you know, you initialize the beta with some value, and afterwards you need to repeat until convergence, meaning until you reach some minima and you're not going anywhere. So, and you're going into the direction which is the opposite of the growth. Okay, so, and how you define the convergence? You define that, okay, that if you are here, the difference between the values of the betas will be large enough, but if you are somewhere here, the difference between betas will be small enough. Okay, so learning rate and why it's important. If you choose, because kind of what determined to us how quickly we jump the hill, this coefficient alpha, which is called learning rate. So if you choose very small learning rate, you will go, but you will go very slow. And it's a legitimate way of going. So if you go very slow, and if you're on the right side of the hill, you will definitely reach your goal. But it might take you a very long time. If you have a large learning rate, you're going to jump there and back, and not necessarily you're going to reach the minimum. So choosing of this alpha is also a separate skill of you kind of as a person who is training machine learning models. So in the same way as we were choosing those lambdas for the regularization, now we also need to choose the different learning rates and choose what of those works better. Okay, so choice of learning rate: if alpha is too small, losses decreasing too slow; alpha is too large, loss could be also increased. So that's why what usually people do, if they play with a fixed learning rate, they just take a family of learning rates and they see how the training is going. But as I mentioned to you, in the case of a little bit more involved architectures as neural networks, all the standard neural kind of the packages for training neural networks, whether that's TensorFlow or whether that's PyTorch, they both have a system where you can have a what is called the scheduling of the learning rate. Also, you can say that, okay, for the first 100 iterations of the training, use this learning rate, and afterwards you can decrease it in a step fashion, or you can decrease it, for example, exponentially or something like that. So, this is called scheduling, and that seems to be working very good. And you can understand also kind of intuitively why you want to do it, because in the beginning, you never want to be here, but you want to do a bigger jumps. But as you get into the good points, you want the size of your jumps, you want to decrease them so that you're settling down nicely into the minimum. So, and that's where all sorts of scheduling of the learning rates are very useful. Okay. So, comparison of the strategies, of course, closed form solution, no hyperparameters, but slow if the number of it's very slow if the system is large. The gradient descent, we get extra one hyperparameter. So besides our regularization parameters, we also get alpha, which we need to play with, but it scales nicely. So we can solve the very large problems using that. Okay, so what do we have here? I think here we just, the same, but with the regularization. So I think that we can just skip it. And those of us who's mathematically inclined, they can go over it. And I think let's go to the, oops, Benjamin, sorry. Okay. So let's go, because now we know how we're going to train betas, because that's what we need. We're going to go to the very simple example. We're going to break everything what I told you, but we're just going to learn something about that. And afterwards, we're going to have an example where we're going to do a little bit more accurate hyperparameter tuning. Okay? So let's go into the Python. And I have here the example. Share. So you need to download from the canvas these two files, yes, linear regression practice with a task, and I will tell you what the task is, and this file of the data set, USA housing data set. It's a very standard example, very naive, but we need to start somewhere. Okay, so in order to run this notebook, we need to have a NumPy pandas, which you will probably have. We need to have a matplotlib, and we need to have this Seaborn. Seaborn is something like matplotlib, but more for the data science. And somewhere down the line, we will also need scikit-learn. We're going to code scikit-learn, and we're going to call a couple of functions from there. So everybody have it. Can you just do thumbs up in the... There is a question, but I'm not sure that I know the answer. I don't know what is a nested cross-validation, sorry. Okay, so there is a kind of, I also added the link where I took that notebook, because I'm not the inventor of this notebook, and this is very, very naive one, but let's go into this. And what we're going to do, so first we import all the functions. Afterwards, we import the data set, which you've done in the standard pandas way. Yes, and of course, the task is based on all the input features. We want to predict the housing prices. And this is a absolutely standard vanilla data set, and you can find, on Kaggle and other resources, zillion examples of how to deal with such data set. But let's just see some basics which we need to check. So what we can check the data frame info, and I assume that you have a last week pandas, so you shouldn't be surprised, yes? So we can check, some statistical data about the data which we have. So we can do the df describe, and we can see, what is the characteristics, what is the number of entries. And first of all, what we can see, luckily, that the number of entries for all the features is the same, which is very good. Yes, so it means that we don't have an empty features. We have some mean values, standard deviation, minimum, maximum, and the corresponding quintiles, Okay. So we have our columns, average area income, average area house age, average area number of rooms, and so on. And that's where we can use the seaborn, so we can plot the correlations between the corresponding entries. Yeah, and we can see which features are correlated and which are not. So, and of course, the feature with itself is Gaussian correlated, or kind of is correlated. We just get a distribution with the data because this is obviously not Gaussian, but if it's some real number, just by statistics, it's very likely something like Gaussian. But the off diagonal correspond to the cross correlation. And I don't know, have you seen these kind of plots at the pandas? The correlation plots. Could you zoom in your notebook? Okay. Is that good enough? Okay, so and I hear. So what is this table, a big table of the graphs? What does it tell us? For example, let's take these two input things, price and average income. So it just take, all the inputs and plot where is the price and average income. And what we can see that, the price of the house where the people live in US is, roughly, it looks like a linear regression, but, the fatter one, it's a straight line, but the fat straight line, so to say. So roughly speaking, what do we see? That, that the higher the price where the people live, the higher the average area income. Yeah. So, and on the other side, what we can see, for example, that many other things are not that correlated, like, for example, average area income and area population, all over the place. There is definitely not kind of like one-to-one relation. So kind of like you can much more difficultly, it's much more difficult to say how it's related to each other. But, again, certain features are more correlated to each other than other features. Okay, but this is just a nice thing with not just with the one comment. Using that seaborn, you can just see immediately this correlation between all your input of your data set. Okay, but this is just, it's a pre-machine learning thing. So this is just what is called the exploration of what do we need to do. So let's see how the distribution of the things which we need to predict is looking like. The price. Yeah, so we can check that the price, we can plot the histogram, yes, and we can plot the histogram very easily using pandas. Yes, so kind of DF price. So DF is our data set, yeah. Where it was DF read US housing. So DF price will give us, what it will give us? It will give us values of that column, yeah. And we can do DF price dot plot dot hist. And we can get, 25 beans. So we can change the number of beans to get more finer, more coarser distribution. Yes, if we, and it will take just all the prices and just put them, how many interests for each price you have. And we see very nice kind of Gaussian-like distribution. We can split it into the 10, but 25 is good enough. Okay. We can also do some other types of plot, for example, plot density, but, if you do DF price dot plot, we could get, all sorts of options. Will we get? Yes. So all sorts of options how we can do the plotting. So when you're welcome to make experiments with that. Okay. Now we can also plot kind of like, because that was just, this was just a graphical representation of how the features are related to each other, how the entries of our tables are independent, not independent, but we can formally characterize it. So we can build something which is called correlation metrics. And this is built-in feature of the pandas again. So, and obviously, average area income is perfectly correlated with itself, but we can also see that, that, for example, average area house age and average area income is a little bit anti-correlated, and average area income and the price of the house is quite strongly correlated. Yeah, and we can plot it as the heat map. Yeah, but this is again, this is a standard thing so that we can plot it. So where 0 means kind of the dark means 0 and this bright means perfect correlation. Okay, so next, now we need to slowly come to our machine learning task. Yeah, so what can we do? So first of all, we can get the list of columns. Yeah, we can see that do we need every columns or not, or do we have some useless information for this particular thing, or kind of not useful for this particular task? For example, address and price for now we need to also to exclude, because that is going to be what we want to predict. So, and we can say that, okay, our X is going to be only the columns which are these ones, you know. Yeah, so this is our input data and output data is price. Yeah, and we can check how the X is looking like. So we have an average area income, average house age, average area number of rooms, and so on. Average area number of bedrooms, area population, and prices are here. Okay, so now what we need to do, now we need to start with the machine learning task, because now we want to learn to build a model which is going to predict the price. And as I mentioned to you, kind of, and I was telling that, oh, we need to training, validation, and test, but let's do something very simple. Let's do this first training, test and train split. And for that, we need that scikit-learn model, and this have a special function, which is called train test split. So we need to load that function. And we just do the test train split. So we do X train, X test, Y train, Y test is a test train split of X and Y. In this case, we choose 70% for the training, 30% for the testing. So that's why the test site is 0,3. So it's 30. If you want 80-20, so you need to put 0,2. If you want 60-40, you need to put 0,4. And this is also the option which you can play with while you're training your model, because this is also might be affecting how good or nice is your training. And, you know, for reproducibility, so that your code is producing you the same results for the same data, for the same model, you want to fix a random number, which you're going to use, because you're supposed to know that computers cannot generate to you random numbers, truly random numbers. Because to generate truly random numbers, you need to use some physical principles. And with the computers, it's rather difficult. So you can use, for example, quantum mechanics to generate truly random numbers. But you cannot generate a truly random numbers on the computer. And the computers always generate something which is called pseudo-random numbers. So it's a sequence of numbers which looks like random numbers up to a certain point. But they are good enough, so to say. So, and by fixing this random state, we're just making sure that the sequence which is generated is going to be the same. So if I'm going to get some number by running this code now, if I'm not, if I fix this state of the random number generator, when tomorrow I will run the code, I will get the same number. But if I don't fix, it's going to pick for the splitting different random numbers, and I might get a different answer. So, and I will get a problem which is called reproducibility, because I really want to be my results reproducible. So, like, you know, for example, for academic purposes, it's good to fix these things. Okay, so we just run it. It's have done the split, and now we can check what is the size of the test train. Yes, so we have 5,000 entries initially. Yes, with our 5,000 entries, 5 features. So training is 3,500 with the 5 features. Test is 1,500 with the 5 features, and of course the corresponding prices, 3,500 and the 1,500, which is good. Okay. So now what do we need to do? Now we need to take from our scikit-learn, and that should be the package which you need to learn how to use and learn what does it have inside. We need to import models, and in the next tutorial we're going to also use scikit-learn, but to get the different models a little bit more involved. And now it's going to be vanilla linear regression without any regularization, because in the moment when you get regularization, it will be called different models. Okay, so we just import linear regression and we import metrics. So, and now it's very, very simple because it's one and the same syntaxes. So you import in the model family. So you create it, we call LM, linear model is linear regression. And now what we do, we just do LM fit. And if you imported some other model, for example, random forest, or you imported something else, you still will do the same thing. Model.fit training data. Oops. And your model is fitted. And now you can check what is the values of the linear terms, which it's find out, and it's find out, the intercept term is equal to this, and the other linear coefficients, 5 of them, yeah, because we have 5 features, are equal to these numbers. So we can put them also to the data frame, and now we can, and now there is an interesting question. Now what we can do, now we can plot the following thing, and let's try to understand what it is. So what are we plotting? So we're plotting the scatter plot of the features vs price, and what we can check how price, and we haven't yet kind of have done any predictions, but how price is related to other features. It's something like we've done here, but only vs price. Here it's everything against everyone, but here it's only against price because we're interested in, because the price is what we want to predict. Okay, our model is trained, and what we can now do, now we can also see what is the R2 squared fit of our trained model. So we can get R2 scores. That's why we were importing metrics, and R2 is 0.19, which is good enough for this simple thing, because you see, I haven't done anything which I told you. We haven't done normalization of the features. We haven't done we haven't done regularization. We haven't done cross-validation. So we haven't done anything, but this is just to give you a sense, how easy it is. And in the next tutorial, we're going to do a little bit more to make it a little bit more involved. Okay. So we can check that, that now we can, let's predict. And again, the prediction is absolutely standard thing. So is model.predict, and you input your data which you want to predict. And now we can check how good or how bad it is. We can check what is the dependence between, we want to plot a scatter plot between the test data, the true answers, and the predicted answers. And even without doing any things which I told you, it's such a simple data set that we get quite a good agreement. Yeah, because it's actual prices, and this is predicted prices. And, in the perfect case, it will be line y is equal to x. And it is more or less line is equal, y is equal to x, but with a little bit of wiggling space. So it means that, linear regression work pretty well for this kind of data set, which is relatively simple and straightforward. And now we can also calculate, all the rest metrics which I mentioned to you. We can calculate it on the test data. But you see, the problem is because we haven't normalized the data, these numbers look a little bit inconclusive. It's not clear what does it mean. Is the mean absolute error of 81,000 is it good or is it bad? We have no idea, and that's why R2 is a little bit better characteristic. And R2 on the training data was 0.919, and on the test data it 0.915, which is good enough. And stop. Why? Sorry, I'm showing you. Okay, so but you don't see this. Let me close that. That's what I want you to do. Sorry. Because this is already with the answer. Sorry, guys. Yes, because your notebook is finishing right here with 0.15. But what I suggest you to do is the following, because on this graph, what we've seen that some of the characteristics of our data set are completely useless. For example, this one, average area number of bedrooms vs price. Yes, because, for the 2 bedrooms, we have price could be anything in the range For 3 bedrooms is also roughly anything in the range, and so on. So, and your task is now to redefine the training set without this one and to do retraining. And meanwhile, there was a couple of questions. I'm getting error when trying to run correlation metrics and heat map cell. Correlation got an expected error. If the argument is numeric only, it means that you have included in your data set the address. You haven't dropped the address. Just check, because it can do the correlation only for the. Just check what is your data to which you're plotting the. You're plotting the heat map. Does random state has a relationship to the train test ratio? No. Random state have a relationship to what kind of sequence of the random numbers are you getting. Test train ratio is thing which you define. I mean, and this is you choose. You know, in this example, it's 0.3, which means that 70% training, 30% test. But what this random state is doing, the random state is telling you kind of like which kind of entries from your total data are going to go to the test set and which are going to the training set. Is it clear or not? Because how you would define, you know, you have 100 entries, yeah? And you need to take 70 into the one bucket and 30 into the other bucket. How you would define item number 1? Do you put it to the training or to the test set? You need to draw a random number and you need to decide where you go. And the sequence of those random numbers which you are getting when you're drawing, that's what fixing the random, that is what is fixed by random state. If you don't fix it, every time it's going to be different. And there is a space for that. But if you want that your code is completely reproducible, it's good to fix it. Okay. Not sure about why we have an image. Okay. So what does the parameter random state 42 do again? I do not hear. Okay, I just explain. I hope. Okay, there is a people answer. Yeah, you can choose 1 to 3. You can choose 2025. You can choose 21. You can choose 1. It's just fixing the sequence of the random numbers. If you don't get it, just forget it, and you can skip it. But the problem is that, you know, in the moment when you report the results of your machine learning as the code which produces certain results, this code is supposed to be reproducible. And what does it mean, the word reproducible? It means that, you know, when I take your code and run, and when you take your code and run the next time, it's supposed to give one and the same result. So that it's not some random fluke of something that you get a nice result today. But that is happening all the time. And what does it mean as well? So that if you're going to draw something which is undeterminate as a sequence of random numbers, because what is the sequence of random numbers? Is 0,1, 0,2, 0,23, 0,7, 0,9. So when you write random state is equal to 42, it means that, you know, I run the notebook and I draw the sequence, and that will be the sequence of my random numbers. The next time it will be the same sequence. Okay, I'm not sure why people post the sigmoid image, but okay, let them do it. R2 value implies the accuracy of the model. Yes, R2 value implies something about model, and the R2 is supposed to be close to 1. And we are good enough. You know, if R2 is close to 1, it means that we are good enough. Validation is not included into the split and test here. Why? First of all, validation is not included because we don't have a hyperparameters. We don't have regularization. Why we introduce validation into the, besides the fact that, you know, I told you that this is a very simple example, but also why we introduce validation? Because we use validation to fix value lambda. But here in this model, there is no lambda. Please explain the significance of mean absolute error, mean squared error, root mean squared error. It's just a different ways to measuring loss. And that is all. There is no significance. And in this particular instance, that's what's supposed to go down as you train the model, but there are different ways of measuring this loss. What are the criteria in determining random stain? There is no criteria. You can write anything, but as long as it's written, it's the sequence of the random numbers. Okay, I'm struggling in understanding the question. I was asking regarding reading the data for quadratic function. We can use a sigmoid also instead of linear. Yes, we can use a sigmoid, but I mean, what you give as what is written in the bottom, this would be related to classification. But people use sigmoid as well, and that was you can use a sigmoid as the function if you don't. Okay, this could be used as what is called the logistic regression, and this is another model. Yes, if you afterwards says that if you're above 1/2, you're in the class 1, and you're below 1/2, you're in the class 0. So that would be the classification task. But linear function is just something very small. You can use anything instead of linear function. But in the end of the day, as I mentioned, it is a linear function, because what you want your data to be linearly separable. If you're talking about the classification task, you want two blobs which are separable. And for that, you can use some, tricky features. Okay, have we done the task? Have we excluded supposedly useless average number of bedrooms, and have we getting the same R2 score? Can somebody do something in the Slack so that I know that something is happening, or do I need to give a hint how to kick out the feature which we don't need? Yes, Emmanuel, and what is the question? Okay. Dot drop, yes, it might work. But you can just also, when you do the dot drop, you can just explicitly say the name of the column, which will also work. So where we are, guys? Where we are? So let's try the suggestion from the chat. Because I haven't been running this notebook, sorry. So I was running other notebook. let me run this one. Let's run cells. Okay. Let's see if it works. Okay, so what do we have in X? Oops. Okay, so we have income. Yes, good, that's working. So good. So what are our R2 scores on the test and training data? Can you kindly explain the splitting of the data again? The splitting of the data, you mean what? The splitting of the data in the test and training in this example, or in general, or what's the question? Can you please specify? X training, etc. Are you talking about this example, which we're doing now? Yes? Yeah, I prefer that solution. Yes, good. So I would just, yes, have done drop. I've done drop as well. Okay. So in this particular example, what do we do with the splitting of the data? Where is the splitting of the data? Yes. So it's a standard function of the scikit-learn, so that you don't need to think how to split the data. And this is only the part of the family of possible functions which can do splitting of the data for you. And this is the simplest function, which is just splitting your all training data and all data, all input data and all output data into the test and training in automatic way, so that you don't need to do it manually. So you need to specify the size, because the program, of course, don't know. But, again, we can, and let's do it. Scikit-learn. Okay. Yeah, so scikit-learn train test split. Yes, and input arrays, so your X's and Y's, your data. You not have to specify test size. You not have to specify train size. You don't have to specify anything, because you see it have more functions or more parameters. And if you don't specify them, so you can input list arrays or sparse arrays, what is called, and it will automatically do it for you. If you don't specify the test size, what it's going to do, it will be set to 25%. Yeah, so the same you get about the train size. Again, random state, I spent already enough time discussing the random state, and if it's a little bit difficult to get, for now, you can just ignore that parameter. And in that case, you might get, every time you run the notebook, you might get a little variation in your kind of R2 in this case. Yeah, so there is also parameter whether you need your shuffle data or not. So whether you want, when you do the split, do you want to kind of shuffle it? And stratify is another useful concept, which is essentially making sure that there is, if you're dealing with it's making sure that the distribution of the data in the test and the training is similar. So in general, it's important to do things like that. But as I mentioned, we are doing a very, very simple example. So, and kind of like that's, I don't know what else to explain here, because it just have a function which have a certain, certain syntaxes, and it's do it for you. It's do the split for you. I'm not sure that, if I understand. Okay, somebody is saying that I remove the columns average area house age, average area number of rooms, and this mate are two verse, but you remove two of them. And if we go into the house age, where is house age? Yes, you see, with the house age, I wouldn't remove it because I ask you to remove this one because it seems to be doesn't make any difference. But this one, it seems to be correspond to correlation. So there is some correlation between the average area house age and the price. So because you see, it's not a circle, it's an ellipsis, which is like, elongated along the y is equal to x. Y is equal to x will be like a perfect correlation. You increase here, here is increased. You increase here, here is increased. So it's like, it's not kind of like narrow. It's not like this, how we get here, but of course, kind of this will be kind of like noisy, but almost perfect correlation. And it's good that we have it because it's mean that our model is nicely predicting the values, even such a simple model. But to remove this feature should affect the performance of your model. Because we expect it, because we see that there is a correlation. There is a kind of like trend which is saying that, okay, in most of the cases, as you increase the age of the house, the price is rising. Okay, train model, try model fit, X train, Y train. Yes, and have the model been trained? And Jeremy, how much? And whose model? Which error have you got? The model could not convert string to float. Ah, yes, because, but it means that you still have address somewhere. Because this definitely looks like an address. So somewhere in the X train, you still have address as the feature. So something went wrong somewhere. Because this is clearly address. And yes, up in the chat, I only now seen somebody indicated that, a lot of questions for the simple questions in machine learning you can get from ChatGPT, and the ChatGPT will do it better than I. So how are we doing with the R2 scores? So in my case, yes, I've done the, just X train and X test, because just to keep everything is the same reshuffling, I just done the drop of the corresponding columns, which is, again, is straightforward thing to do. Yes, and in this case, I don't even need, so I really, in that case, kind of like, when we do it on the level of the data frame, it's okay. But the problem is that we need to do again splitting, we need to do again all of the steps. But in this case, we just need to get rid of one column, average area number of bedrooms. So we can do it. Yeah. And if we have done it, we can just create a new model, do model fit, because train and test data is changed, but the Y's are the same. So we can look on the characteristics, and we can calculate the R2, and we see that R2 on the training data is up to 3 commas is the same. We get, again, a little bit horrible value of my MSE and RMSE. But as I mentioned to you, the only reason is so that it's a little bit inconclusive, only just because we didn't scale the data. Yes, and afterwards, what we do, we get R2, and R2 is also the same value. So it's really at least to the 3 commas after the zero, we can see that, you know, this feature is rather speaking useless feature. So kind of like it's have no effect on the housing prices, at least into this precision and in this model family. You know, if we have done more precise model, because again, R2 is not 1, is not 0.99, I'm sure that you can make it higher. But of course, you know, the question is how to make sure that we're not overfitting. So that's again, is a separate investigation. But kind of like just pure optically, this feature is not really telling us anything, because all the rest, you can see the trend, you know, this is a correlation. So you increase something is also increasing. So it seems like, but this one is not really informative. Okay, so, and you can try to make it better. And you see, I started doing it as well. So, because I mentioned to you that these numbers are inconclusive, but we can try to make them conclusive by doing what? By standardizing data. And in same scikit-learn, there is a function which is called standard scaler. And the standard scaler, again, so we can ask ChatGPT, or we can ask scikit-learn. We can just read documentation, and we can see what is the standard scaler is doing. And standard scaling is doing exactly bringing it to it's subtracting the mean from the value and dividing it by standard deviation. And it will have some nice, it's supposed to have some nice examples of how it's applied. So we have some data, we create a standard scaler, we feed standard scaler with the data, and we transform the data. So, and that's what you need to do if you want to try to do the same linear regression game. And you see, in this particular problem, it's very nicely telling us that, you know, maybe we don't need, you know, fancy neural network to predict the price of the house in this data set, because the model is the data is so simple, so that very simple linear regression works fine. But as you're going to see, you know, as the models get more complicated, or as the data get more complicated, you need more complicated solutions. But you don't necessarily need a complicated solutions. Okay, so you can try to play it with this, and you see an important point is, which I want to make you aware of, that you need to learn the transformation on the training data and apply it. So you need to learn the transformation on the training data and apply it to the training data and test data. Why you cannot learn the transformation on the whole data, on the test plus training? Can anybody suggest in the chat? Okay. Okay, good. So R2, okay, so. If feature did not affect the R2 score, why do we remove it? Because it means that it's just irrelevant feature. Why? I mean, we can keep it, but, you know, imagine kind of like in general what you can get from these linear models. You know, if your data is normalized, and we're going to see it in the next tutorial, you can get the feature importance kind of sequence. So which features are important and which are not? Because when you're dealing, you know, in this particular case, we could keep it because we have only, you know, 5 or 6 input variables, you know, with address, because, you know, address could be important, you know, if we do some, you know, geostationary modeling and, you know, incorporate that data into it. But the idea is that, you know, if you have a lot of features, you really want to know which of them are important or not, because if you need to train, you know, if you imagine that you need to train one and the same model, but you need to update the training on the huge amount of data, and you need to do it on the fly in real time, the smaller the number of features you can incorporate in your model, the better it is. You know, if you have, you know, 1 million entries, suddenly, you know, the training will take a finite time. And if you can reduce, if you can throw away several features, it will speed up your training. And that is why only now the search engines begins to incorporate neural networks, into the search because training neural networks take time. And a lot of search engines for a very long time, they were not using any neural networks, not because they didn't know about that, but just the additional time which is take to train your neural network on the flies as the kind of the search engine are crawling the web for the new information was just taking too long time, and you needed to update it faster. So, but why in the standard scaler? So if we want to do the scaling, we need to learn how to scale on the training data and apply it to the test data. Why we cannot learn it on both? Why we cannot take the whole data set, find the mean, variance, and normalize the whole data set and afterwards do the split?
The training model could be the same as the teaching model. So if we split them, we can make sure that there's two models.
Not really. Okay, so we can do scaling on both X and Y. We can do, but on Y we don't need to, not necessary. But now the question is why we cannot do scaling, why we cannot calculate the mean and variance on the whole X, why we should do it only on the training part, and afterwards the mean and variance of the training should be applied to the test. We can also do it on Y, but I mean, the logic will be the same. We will take Y of training in some problems, and we do it on the Y of training, and afterwards we learn mean and variance of Y of training, and we apply it to the Y of test. But why we cannot do it on the whole thing in one go? Somebody's typing something? And I'm sure ChatGPT knows the answer. To avoid overfitting. It's a not bad answer. In which sense to avoid overfitting? Not quite. Budget constraints. It's a good answer, but wrong. Okay, so the reason is very simple. What is a test set? Test set is the data on which we only evaluate the performance of the model. So, but when we are taking we calculate the average of the training and test together, the information about what is in the test data is encoded in the value of the mean and variance. Yes, because it's affecting the mean and variance, because the information is there. You know, if you have x1, x2, x3, and x1, x2 is training and x3 is test. So when you calculate the average of three of them, information about x3 is in that number. But that's what you don't want about test, because it's called the data, the information data contamination, because the information about the right answer, so to say, is hidden already. Part of that information is hidden in the training data. And that is why you calculate everything only about the training data and just apply the same transformation to the test data. And what happening to the test in that case, it doesn't matter, you know, if it's not perfectly Gaussian or if it's, you know, a little bit out of range, it doesn't matter. But the information from the test data should never go into the training, because in that case, you are not doing independent testing. You're not building the model, you're not evaluating the true performance of the model on the test data, because the model in some way have already the information about the test data. Yeah, okay, somebody also writes to ensure that information from the test data doesn't influence the model. Yes. Yes, you can get accuracy 100%. What's wrong with that? I mean, it's such a simple model so that you can get it, you know. simple model, simple data set. Is there an indicator that we can use to guide us if the certain features should be included or excluded? Yes, that's coming in the next tutorial, because there is a feature rank importance. And if the feature importance is very small compared to other features, you can just drop it. Okay, so what are we doing? Have everybody managed to get this bit right, or this bit as I have, unnormalized 0,15 and 0,019? Good. Okay, so are we breaking or what? Or should I go back to lecture? Okay. Okay, please note lunchtime. Good. Okay, so lunch break.
I omit.
Okay, so should we continue? Hello, hello, Wani. Should we continue?
Yes, Prof. Let's continue.
Okay, good. Where is my screen? Okay, so in the first half of the day, okay, let me start the video. I told you about the linear regression, and now we're going to talk a little bit about the classification problems, and also we're going to look into the couple of examples of applying, a little bit more fancy regression and a little bit more fancy also kind of like playing with the classification. And that's a plan for the day. Okay, so so supervised learning, as we mentioned, or as I was mentioning to you, yes, we have an input data. We choose the model family. We optimize the parameters of the model. We take in by minimizing of the loss with, with some hyperparameters and so on, and we get a model. Yeah. So, and what regression is doing, it's predicting if your y's are real values. So, but besides that, there is one more type of task, which sometimes you need to do, which is called classification. And what do you need to do in classification? In that case, your y's are not continuous value, but it's a discrete value. If it's two values, it's called binary classification. It's a yes, no answer. So it could be 0 or 1, or it could be, yes, no. But in that case, if it's a yes, no, you usually convert it to the 0 and 1. But sometimes it could be more. It could be, like in this example, from 1 to k. And as I mentioned to you, if we're talking, for example, about the digits classification task, it's from 0 to 9 classes. Yes, is it digit 0, is it digit 1, and so on. So you have 10 classes, and very often you have more than one class. For example, if it's some sort of medical diagnostics, it could be not that it's healthy or unhealthy, but if it's unhealthy, it could be how unhealthy. It's this problem, that problem, that problem. So this is examples for you of kind of like you could easily have a multi-class classification or kind of a single class classification. Okay. So if it's two classes, as we used to have already, you have what is called the binary classification. So, and what is the task is? The task is, in case of binary classification, that you put your data in some hyperspace, whatever it is. In this case, it's a 2D, tumor size and the age, and we can draw a line. So the best possible line would separate our classes. And, if anything falls on this side, it will be in the red class. And if anything falls on this side, it will be in the blue class, So, and kind of the task is, what is the best way of putting this line, which is separating to us, events of one kind from the events of the other kind. Okay, so, and what do we need to do for classification? So, we have a blue points, we have a red points. We need to draw a line, and we need to say that, everything which is above the line is blue class, and everything which is below the line, the line is the red class, so one class, another class. So we need to predict. And what do we need to have? In this case, we need to have, how we're going to define kind of, is this line better than, I don't know, line like this? So we need what is called the loss function. Yeah, and we need to think what kind of loss function we might have. And what is the best way of choosing the loss function, which is also not necessarily an easy question, because in the case of linear regression, I somehow kind of like explain to you, oh, we can estimate distance to the curve, but as I've shown you that it's not only mean squared error, you can have, the sums with absolute values and things like that, and they could lead you to certain mathematical problems, but in principle, it also could be a legitimate loss function. So we need to came up here with some sort of a loss function. Okay, and there are several approaches how to do that. And the very traditional approach, so if you probably ask ChatGPT or something like that, so the traditional approach will lead you to the family of the classifiers and also regressors, which are called SVMs or support vector machines. And essentially, what does it do? It's estimating, kind of like it's kind of the loss function is trying to maximize the distance between the line and the limiting cases. So kind of like, you go along the line and you see for the kind of like, first of all, you can start by kind of like estimating the distance from the misclassified objects. So, we measure the distances, but that will also lead us to the kind of like next question, how to do it. But, we can say, okay, this is blue one is misclassified, so we need to calculate the distance. This is red is misclassified, we need to calculate the distance, and so on. So kind of this is one of the approaches. Yes, and that will give us, some sort of the loss function which one can play with, and that's what is usually used in the support vector machines. And kind of when we draw this line, what we will try to do, because where this line will come from. So first of all, we can try to minimize this distance. An alternative approach in the support vector machines is just you try to draw the line such that so that the points which are along the line are kind of maximally separated. And those vectors which pretend to that maximal separated are called support vectors. That's where this name is coming from. And of course, it could be used for the regression task, but in our case, we're interested in using something like that for the classification task. And in the tutorial, we're going to have a support vector classifier. And essentially, because of universal language of scikit-learn, in principle, we don't even need to understand how exactly does it work. We just need to know, okay, we can just create a model and apply it to our data. Okay. But there is another view on, and this is a very kind of a separate direction in machine learning in general, and it's looking at machine learning from the probabilistic point of view. And it's when you're doing anything what you do in all the learning tasks, your job is that you're trying to estimate what is the probability that given your input the outcome will be yy or yi given the kind of our xi and beta. So we're just trying to estimate what is the conditional probability, and these probability families are defined to us, and are just defining to us, what are we dealing with, what is kind of families we're defining, so on and so forth. And now, kind of like, if we need to talk about the loss function minimization, now we need to kind of like, or kind of maximization, we need to talk about, what are we dealing with? So before we were saying that, okay, so yi is proportional to just, kind of to the kind of the output of the function, but now we're saying that yi is proportional to the probability. And as we're going to see that, the probabilities in this case will be strongly related to those models, because in linear cases, we get some probability distribution, but as we do the more and more training, the probability distribution just become the peaks around the corresponding linear function solution. So, okay, so the intuition is that, this f of beta just provide the point, and this probability provide the score of possible yi's, or kind of just give you the probability scores. And that's maybe a little bit better approach for the classification problems, and you're going to see now why. Okay, so, and if you are talking about the probabilities, we need to talk about the likelihoods, or kind of because how you characterize is one distribution is kind of like related to another, you need to introduce what is called the likelihoods. And in this case, it's introduced like this. So kind of the loss function, if it's just, a probability of all y's given all x's. So what is the probability of obtaining all the list of values of y given all the input data? Because the input data is independent, we can write it as a product of each probability. So what is the probability to get yi given the input xi for the probability distribution kind of defined by beta. So this is good, but the difficulty here is that you need to have, a product with many, many entries. And if you have products, for example, of many small numbers or of very, not even large numbers, but numbers which are greater than 1, numerically that will explode. And the typical trick is, and this is trick, which is used in probability theory, in machine learning, it's used in statistical physics. You go to the logarithms on the quantities because log of the product is the sum of the logs. So, and this is a very typical thing. So, and the log of this, essentially of the loss function in this case is called negative log likelihood. So, and computationally it's much better behaving because it's a sum of things. So even if the things are very small, they will sum up to something small, but controllable. It wouldn't blow up. It wouldn't get to very zero on the machine level, or it wouldn't explode to the, to the number which is above any decent threshold. Okay. So that's the first little clue where we need to go. Now we need to grab this probability thing for the linear models and understand how we can relate it to our things. Okay, so and what is the intuition behind likelihood? So, we have, points on the kind of on some, how to say, in some space, and we want to draw a plane, or we want to draw a hyperplane, because of course here it's a line because we're dealing with, two-dimensional data. But, if you have many, many dimensions, you're not drawing a line, you're drawing a hyperplane. So in the 3 dimensions, it will be plane, in 4 dimensions, it will be another plane, and so on. So, and what we want from our probability of likelihood, we want that the line like this is good line, because we can see that, okay, more or less everybody who is blue is on one side, everybody who is red on the other side. Of course, this is not a perfect line. One can do it a little bit nicer, but it's much better than this line. This is really clear. You cannot say that everybody who is above the green line is blue and who is below is red. This we cannot say. So, and it means that our likelihood needs to be high in this case, and our likelihood needs to be low in this case. And we need something like that. Okay? So, and in order to get the intuition how we can get something like that and why something like that makes sense, let's go back for a second to the linear models. And we can define the conditional probability for the linear model to look like this. It's just a Gaussian distribution where we take a difference between our linear function minus true answer. Yes, what are we going to have? If we have a perfect agreement, this is going to be exactly the center of the distribution. That's what we want. This is most likely event. Yeah. So, but if we are a little bit further away, we'll get, less likely. So, and that's what we want. And we want to have some balances of the more or less likelihoods. And now if we take log of it, what will happen? So if the likelihood for the linear model is looking like this negative log likelihood is suddenly looking like this, which is exactly MSE, which we have before. So, and that should tell you that, okay, so this approach with probabilities is essentially equivalent to the approach with just with the linear functions, because, and this likelihood approach is giving us exactly the same log function which we have before, which is very, very good. And that's kind of like, and essentially what you do, which approach you choose, it depends on what are you dealing with, but essentially, you can go either way. Okay, but here it could be a little bit useful for our classification tasks. Okay, so again, for the linear regression, what we do, we optimize betas so that we're minimizing our likelihood, and this is called maximum likelihood estimation, since we're maximizing the likelihood equivalent to the minimizing of this negative log likelihood. Okay, so and as I mentioned to you already, yes, if we're choosing the linear models family, we're recovering linear function, because when we're optimizing over the all, so what will be the function? It will be this optimization, and that will exactly recover our linear functions. So it's exactly identical. Okay, but now our option is that was particular choice of probability distribution. If we choose another probability distribution, which is saying what is the probability that this value and that value are close, we can get to some other functional classes, and that's exactly what we are going to do. So we need to take a design decisions. Yes, we need to choose the likelihood probability. So we need to choose a function which is going to characterize us. What is the probability of obtaining outcome y given the input data x for the parameters beta, given the parameters beta, and how to optimize this negative log likelihood. So are we going to use gradient descent, or are we going to do something else, and how we're going to do it? Yeah. So corresponding loss minimization view is what is the most likely label beta to be such that this is happening, and negative log likelihood needs to be can be optimized like this. And this is a very nice framework, which is, these probabilistic approaches are very a lot of people, when they're talking about doing machine learning, they're only talking about these sorts of probabilistic approaches, and they never do the things which I told you about the log likelihoods, because those approaches have its benefits. But the approaches which I told you in the beginning, they're just very simple, and that's why other people who are a little bit less formal, they do them as well. Okay, so what can we do about classification, and how we can introduce the classification with such approach? So with the linear regression, the probability of obtaining something was proportional. The probability was just proportional to the linear function under the exponential to the power 2. Yeah. So let's now assume that we have a classification, and for a simple case, we'll start with the binary classification. So what if we say that, just looking on this, that the probability of obtaining 0 given input xi is proportional to this part of the exponential, and the probability of obtaining 1 is proportional to the 1 minus that, or something like this. Yeah, and afterwards, of course, we need to normalize, because the probabilities are supposed to be normalized. And what will be the probability of obtaining 1 is just, this factor divided by the sum of the probabilities. And if we just divide by this factor, we're going to get a very nice formula, which already was in the discussion in the chat. So we get something which is called sigmoid function. So, and we could essentially say that the probability of having class 1 given the input data xi is going to be given by this nonlinear function. And the task is just optimization of these betas. And this could be seen by itself as a regression problem. And of course, in that case, your regression value supposed to be between 0 and 1, because I think the graph of this thing is coming just now. Okay. So first, this one, and the probability of 0 is 1 minus this, 1 minus sigmoid, and you're going to see that it will be the same thing, but with a minus sign here. Okay, and the sigmoid function have a very interesting and useful shape exactly for that. So it looks like this. Yeah, so it's in 0, it's 1/2. And for the positive argument, it's monotonously increasing till 1, and afterwards it's asymptotically 1. And for the negative arguments, it's monotonically decreasing until 0. So it's a function between 0 and 1, so it could be perfect. It's a perfect candidate for the probability. So that's the first thing, an important thing, so that it's really could be used as a probability. Yeah, and it's relatively straightforward to deal with. Okay, so, and as I mentioned to you, this, if we don't even talk about classification, this family of models are called logistic regression. So if your entry is bounded between 0 and 1, instead of linear model, you can do a logistic regression model. So essentially you do linear model under sigmoid. And because it's non-linear model, from this perspective, it's have a little bit more power than the linear model. And this also could be seen in some examples. Okay, so, but if we want to see it as the problem for the classification task, we need to introduce some decision boundary to say that when we are considered something is of the class 1 and something of the class 0, and the most natural choices say that, okay, sigmoid is always between 0 and 1. So if it's above 1/2, it's a class 1. If it's below 1/2, it's a class 0. As simple as that. And although it's very simple solution, and one might think that it's a little bit naive solution, it's extremely powerful and it works. And in a lot of neural networks, sigmoid is exactly the last layer. So it's doing some transformation, doing some things, but in the very last layer, you get a sigmoid, which is exactly doing that. You above 1/2, you're class 1, you're below 1/2, you're class 0. Okay, can we play sigmoid games if we have more than 2 classes? So if we have 3 classes and we want to draw a 3 decision boundaries and so on, can we do it? And the answer is yes, but with a little twist. So we can just say that the probability of obtaining the object in the given class is proportional to the e to the beta x. And in that case, that the kind of the probability is proportional, but overall the probability will be equal to corresponding all the corresponding e to the beta x's with coefficient divided by the sum of all of them. And this quantity is going to be normalized to 1. It's always positive. So it's also good enough probability distribution. And in fact, this is also defined to use an object, which is kind of, it's a standard layer in the neural networks, which is called softmax layer, which is giving you what is the probability of obtaining objects in these K classes. So, and to calculate it, it just do for the input value Z1 to Zk, it's just calculating the corresponding fractions of the exponentials. And what you do afterwards, you just do the max voting. You see probability for which class is the highest. And in that case, you say that the object belongs to this class or to that class. And again, this is a standard, it's a standard bit in the all neural network packages. And this is a standard layer. So we're going to have, for the MNIST, we're going to have a softmax layer in the end. Okay. Okay. So somebody is asking, what is the non-IID data? I do have a response. Okay. So the people already answered, but for those of you who also don't understand what does it mean, that's essentially when you have a data which is IID, so it means that it's independent, what is it? Identical and independently distributed. So it means that, you know, they're completely independent and they are essentially for all practical purposes, they are coming from the Gaussian distribution. But and they satisfy very nicely central limit theorem. So, you know, if you take average over too many of them, you're always going to get Gaussian distribution. But in fact, in the life, you're not always dealing with that. And that is another thing about mathematical aspects of the machine learning, that very often all the proofs which are done, they are done for the IID. So kind of essentially, you know, independently distributed variables, which, you know, if you're dealing with the real life, and because in that case, you can use a central limit theorem to prove the statements. But in fact, in the real life, it's not always the case. But, you know, central limit theorem is also kind of have a wider application range. Okay, so let's go to our multi-class logistic regression. So we can also define the family like that, again, in the same way. And again, it's absolutely the same. Okay, so now we need to talk about how we can say kind of what is the accuracy, or what is the classification metrics for the classification task, you know? So one can talk about accuracy, yes, and accuracy is just counting, you know, how many times have you classified something correctly or not correctly. And the problem with that is that, you know, sometimes, or very often, what you are dealing with something just called imbalanced data sets. So you have a one class number of the entries of the one class is different from the number of another class. And in that case, you need to do some special tricks to make it balanced. But also the question is, you know, how else can we characterize our accuracy? And it's very common in the medical literature, so that, you know, you don't just look, you know, how many times you manage to say things right or say things wrong. So you do a little bit more. So you kind of you add a little bit of more gradation. So, and you can introduce the notion which is a true positive. So it's actually positive and predicted positive. So if your model predicted something in the class 1, and it is in the class 1. So true negative is a predicted in the class 0 and actually in the class 0. This is called true negative. So false negative are actually positive, but predicted negative. So it's actually class 1, but predicted to be class 0. And false positive is actually negative. So it's actually class 0, but predicted to be class 1. So, and accuracy, the problem with accuracy is that it's summing up, you know, all the successful predictions. So it's true positive plus true negative. and divided by the total number of tries. And when you're dealing with a rather imbalanced data set, or you can have some other problems, because sometimes you want that, for example, that, I don't know, that you want to minimize false positives. You not only you want high accuracy, you always want high accuracy, but you want to minimize false positives, or you might want to minimize false negatives only, because it's more important by whatever reason in your particular problem. And in that case, these kind of extra gradations could be very useful. And based on these ones, people introduce the following structure, which is called confusion metrics. And again, we are going to construct them. So confusion metrics is metrics like this. So we have a true positive and true negative. So we have a actual class yes, predicted class no, false negatives. Actual class no, predicted class yes, false positives. Okay, so this object is called confusion metrics. And now based on and for example, the example is, if we have a 3 true positives, 37 true negatives, 4 false negatives, 6 false positives, accuracy is 0.8. And one would think that, it's a very, very good classifier, which with 80% probability, or kind of with 80% accuracy, is predicting to you something correctly. But if you look here, and if you remember what is a true positive, and false negative, you might think that maybe not. Yes. So, and in order to deal with this imbalanced metrics, we want to disentangle this, accuracy on the positive examples and accuracy on the negative examples. And, people do the different splittings, and they will have a different meanings, and in the different domains of science, it have a different applicabilities. Okay, so, and there is a standard terminology. So there is a sensitivity. So it means what is the fraction of the actual positive are predicted positive? So good sensitivity, is if you have a disease, so the test correctly detects it. Yeah. So it's called a true positive rate. So you want to know that, out of, if you take in the test, what is the probability that you are going to if you have a disease and you're taking the test, what is the probability that the test is going to tell it to you? This is rather important information. And there is another thing which is called sensitivity. It's what fraction of the actual negatives are predicted negative, which is also could be important in a certain situation. Yes, if you don't have a disease, that test is also saying that you don't have a disease. And this is very commonly used in medicine. And for example, for the all tests, which you can see if it's a good test, it should be usually it's writing what is the sensitivity and what is the specificity of the corresponding test. Okay, so what is the sensitivity? It's giving you what is the fraction. So what is sensitivity? It's a true positive plus false negative. So it's actual class yes. Yes, and how many of those actual class yes have been predicted yes? So this is sensitivity. And specificity, so how many of the actual class no have been predicted no? Yes, so kind of a true negative or true negative plus false positives. So false negatives are actual class yes, but predicted no, and the false positives is reverse. So in this plays quite an important role in medicine and in the tests. And sometimes you really want, from your test, you want only one bit to be higher than other, because sometimes you train the model and you look at your confusion metrics and you see that that maybe your accuracy is fine, but you get some imbalance in these true positive or true positives and the false so false positives and the false negatives, and you might want to play one of those. Okay. So what does it mean by different definitions are possible? What do you mean that different definitions of what possible? And add sensitivity and specificity values similar to the bias values. Not really. No, because the sensitivity and specificity is exactly this. You know, what is the sensitivity is what is the fraction of actual positive cases are predicted to be positive, and specificity, what is the actual of the negative cases are predicted negative. So it's just, you know, if you compare it to accuracy, it just gives you a slightly better lens on the accuracy. So because accuracy, you see, it's a true positive plus true negatives. So it's kind of like it's averaging out. And this sensitivity and specificity, and you can do also, you can do something like this. You can do it vertically, and it will also have some mean. They just give you a better optics on what you are dealing with. And if we have a medical people in the class, so they can tell you that, you know, how specificity and sensitivity are important in the medical profession. Okay. So again, our example with the 80% accuracy. So we can calculate, and we're getting that, you know, sensitivity is very low of the test. Yes, 3/7 is below 50%, while specificity is quite high, you know, 37/43 is, you know, so you could really see that, you know, what this little confusion matrix allows you to do, it allows you to better zoom on the problem which you are dealing with and telling you that, okay, how many kind of like the details about the kind of class 1 and predicted to be in class 1, how many class 0 and predicted to be class 0. It just allows you to separate these values. Okay. And there is another way to slice it. You know, there is precision and recall. So recall is what fraction of the actual positive are predicted positive. Good recall if you have a disease when the test correctly detected, also called true positive rate and sensitivity. You see, it's kind of in the different places, it's have a very simple, kind of a very similar definition. And precision is what fraction of predicted positive are actual positives. So you can slice that information in the way you need it or when you like it, or your problem is dictating it. Okay, so again, recall is exactly the same as a sensitivity, but precision is that. Yes, so kind of predicted yes, but actual yes out of predicted yes. So you want also to know the precision of your test. But think about that, you know, for this kind of classification problems, it just give you kind of like a better way to analyze, a more detailed way to analyze what exactly are you dealing with. That's all. Okay, so we can do the calculation again, and we can get that, you know, this precision and recall for our example are both quite poor, which was also kind of like clear from the example, although the accuracy is 80%, the fact that, you know, we have the majority of the true negatives, so it means that negative and predicted to be negative, it was really kind of like dominating the accuracy statistics, and, you know, to having some fine grain approach would make our analysis better. And that's, you know, that's a ways how to make the analysis better. Okay, and I think that's it for this node. And I think let me go to the next day node, because what is our plan? Because tomorrow I will only have a half day, and today is okay. So we'll have a break at 3. So yeah, let's go to the next day node, and after the break we can do the little tutorial. Okay. Let me quickly change the slides. Okay. No, that's sorry. Ah, Where is... Okay, preview. Okay, so you should be able to see my screen, and I'm very briefly going to mention to you some other machine learning approaches which are there, which you can also see in scikit-learn, and which we can play with, and it's just for the generic information, and on the examples we'll see how it works. Okay, so what we're going to talk about, or I'm going to talk about, is about kind of nearest neighbors approaches and the decision trees. And decision trees are a very powerful approach to do the classification, to do the regression, and create a neural network before we learn how to train very nicely neural networks, and before we learn to put it at scale. Decision trees was the weapon of choice. If you have a large enough data set which you need very quickly to do the classification or regression, people would usually build what is called decision trees, but they will not just build the one tree. They will build many trees which are called decision forest or kind of random forest and so on, and they would apply the kind of the machine learning techniques to train them and do the predictions. And again, it's all part of the scikit-learn, so we in principle it's good to understand where it's coming from, but we're just going to do the same thing with that in the practice. We're going to do the model fit and afterwards optimize the parameters. Okay, so kind of like these these kind of approaches are called, we have what is called parametric learning and non-parametric learning, and and the parametric learning is just when you have a parameters which you optimize, but also you could have something which is called that when you don't have a parameters, and the learning is just doing something with the model. And the typical example of that are these nearest neighbors and decision trees. And so if we're dealing with the binary classification, and we have a problem for the binary classification, so we have a height, weight, and we need to decide which t-shirt size t-shirt should it be. Yeah, so we can put height and weight, and we have here the t-shirt size, and now the question is how we can solve this problem having our data. So we have this is a medium, and blue are large. Okay, so what do we need to do? So we have some input vectors, we have two features, we have a number of entries, and in principle we can try to play the game which I've shown you in the previous slides. But what we can do now, we can say that, okay, so it's not that difficult problem. So because, I mean, naively speaking, what we can do, we can just draw a kind of box here around height and says that, okay, so if your weight is above something, so you very likely need a larger t-shirt, and if your height is above something, you very likely need a bigger t-shirt. And you see, we don't have even parameters. We just have a condition on our input data, and that's why it's called non-parametric. So we don't have, we don't multiply by some betas which we're optimizing. But now the question is how we put these boundaries. Okay. So yes, we have some input vectors, we have some labels which we want to predict. And the question is, if we add in a new point here, which t-shirt is going to be? Is it to be a large or medium size? Good. Okay, so, and what the K, and we have, first we're going to talk about the K nearest neighbors. And this is just a very simple idea. It's saying that, okay, so how we're going to decide? We're going to say that, okay, so we're going to estimate the distance between this new point and certain number of the neighbors. And we're going to see that, okay, so if, nearest neighbors to this guy are the red guys, we're going to say that this is a red guy. If the nearest neighbors to this guy are the blue guys, so it's going to be a blue guy, as simple as that. So, and although it seems to be a very naive idea, in certain situations, it works very powerfully because it just creates for you, classes. It just automatically works. And the procedure of training is very easy because there is also no training because you just estimate the neighbors. Of course, you need to pre-calculate the distances and afterwards to calculate the distance to nearest neighbors, but there is no formal training, there is no gradient descent, there is no learning rates. And this is a very appealing idea. Okay, so to predict category Y of new point X, find k nearest neighbors according to some distance metric, and assign the majority label to a new point. Yeah. So predict the value to predict the numerical value y for the new points x, find the neighbors and the average value. Good. Okay, so what will be the value here? If we say let's include 3 neighbors, obviously label is blue. Yeah, because for the 3 neighbors there is a 2 blue and 1 red. If we do 5 neighbors, 2 blue and 3 red. And the question is, when we decide how many neighbors we need to have, and what does it mean? That we need to define what the nearest mean, and how many neighbors we think that it's reasonable to take into account. So, and for that we need to define the notion of the distance, and there are different notions of the distance. And for those of you who are a little bit mathematically inclined, you can recognize that there is L1, L2, and L infinity distance. But again, this is the parameter which you can choose in the algorithm, how you assign the distance. So you can try and do it according to the different distances and see which works better. Okay, so in different distances, we'll produce the different outcomes, because you see, this is the example of the decision boundaries for the different distances, meaning that, if we add a new point somewhere here, it's going to be definitely orange. But, for the different distances, there's kind of those cases which are a little bit on the edge, could be a question. So this is playing a role, and you just need to see which of those distances, not only number of neighbors, but also which of those distances are performed better on your test data. Okay, so, and but also the distance approaches are interesting in that way, so that you can also apply to the text, or for example, in this case, you can apply to the character information. And there are some special distances, for example, which is called the Hamming distance, and this is just counting how many characters are the same and how many characters are different in the 2 sequences. And this is a very famous approach which is used, for example, in the genome sequences. So if you get 2 genome sequences, and now you need to decide how these 2 genomes are close or far away from each other. So what you can do, you can just you line up those 2 genomic sequences, and you just see how many base pairs are the same and how many of them are different. And this is very commonly done when you need to build a relationship between the genomes, and you need, for example, build what is called the phylogenetic trees. So when you need to build the trees of how different species are related to each other. And there are several other ways to calculate the distance. So this just to show you, so that you can calculate, when we're saying the distance, it's not necessarily means the Euclidean distance or something based on that. That is the simplest possible case. You can define distance in the multiple ways, and they all will be legitimate ways, and they will all work. And from mathematical perspective, there are some just requirements of what could be called distance, but we're not going down that road for now. Okay, so one more thing, that feature scaling, also kind of like having features which have a different scales, is affecting also the distance. Yeah, and it means that it will affect your nearest neighbors. So if you have features which are looking like this, which are not scaled, kind of this is your some sort of example of original features. So x1 is between 0 and 5, but x2 is from -10 to 50. So your data is split like that, and it's going to affect the number of nearest neighbors. But if you do the normalization of your data, suddenly you get much more nicer distributed thing, and now you can start making decision who belongs to which class. So also keep in mind, although we don't need to do the formal training procedure, so we don't need to do gradient descents and things like that, you still need to do the data normalization. Otherwise, you might have some inconclusive results. Okay, so the problem is also with the distances is that, it gets more and more difficult to calculate distances, and also problems of interpreting of the distances as you increase the dimensions. Because with the dimensions, with increasing of the dimensions, everything becomes more difficult. As you increase the number of dimensions, and this is, have a standard the curse of this dimensionality is not only related to this calculation of the distances, it's related to the generic machine learning problem that the more you increase the dimensions, the more possibilities you get, but more difficult is, for example, to estimate the distances. And for example, the typical example is what is happening to the d-dimensional sphere of the radius r that lies beyond 0.99 of r from the center. So kind of like, what is that little shell outside? What is the percentage? In the dimension 3, it's 3%. In the dimension 100, it's already 63%. And in the dimension 1000, it's already almost everything is outside of that distance. So which of course is a very, very interesting fact observationally. So it means that, that our intuitions about the distances in the multiple dimensions is a little bit flawed. So one needs to take it carefully, but also with the dimension, there are several other effects which are related to the distances, which makes things difficult and which one need to carefully take into account. Okay. So what parameters can we learn? So think broadly, parameters are everything required to produce the output for the given model class. So we have a model class, parameters, new input, predicted y. So KNN classifier. So we need to use the full training data set to predict something. Yes, but also these are methods called not parametric, but the fact that you need to use the all training data to calculate the distances, it will grow, the number of calculations will grow with the size of the data, and it's also, although it's a non-parametric, it's also have its difficulties. Okay. And essentially with the k nearest neighbors, as you understand, it's non-parametric because there is no parameters, but it's still, and in some cases it works, in some cases it don't. And the generic rule is that you have a sequence of methods and you just need for your problem to try one after another and see which works. And that's what you need to use. Yes, this is have a scalability issue. You see it's tend to work in practice. And what else is working in practice with the k nearest neighbors is, again, the feature map. So you do transformation and you change your space and you estimate the distance in that transform space. That seems to work very nicely. Okay, so now let's go very quickly. Okay, let me see into the chat. And afterwards we'll go very quickly into the decision trees which are much more powerful. Yes, I will share the slides, of course. What if we choose even number? We can choose even number, but the problem with the even number that if you get two here, two there, you don't know which decision to take. So in that case, you need to decide what you're going to do. If it's two blue case, to blue set, to red set, what are you going to decide? It's rather difficult. Yes. Yeah. It's the correct answer is that they're likely to give a tie. Yes. So that's why you want the majority vote to work. And that's why you want odd numbers. Okay, so, and to the k nearest neighbors, trees are really extremely powerful approach. And the trees are, or decision trees, how they're built, they're used everywhere. And in the moment when we think about constructing of algorithm for anything, of like something which have some set of the variables, very often we would naturally build decision trees. Yes, for example, this is an example in medicine. So number of days with fever before smaller than 2, larger than 2. So no problem. The child age is above 3, below 3. So you go one by one. Yes, so and these kind of trees exist, or decision trees exist everywhere. And it's naturally that the people do it. Yeah, but the question is, how can we do it in an automatic way? And the idea is that, yes, that you want to be using your data, you want to construct in a little automatic way. So, and exactly what you wanted to do, you want to build your tree on the simple test, greater or equal than 2, smaller than 3, or something like this, true, false, and that you can go down the tree and get your decisions. And you grow the tree top down, and kind of like and now we're going to talk about, you know, how we can came up with this split point and how we do the split point. But you invent the test, you find the limiting test value, and if it's true, you go to one branch. If it's false, you go to another branch, and afterwards you do again with some other feature. And usually you do it with features. And I think it should be here, but before that, the intuition, because it's going to be a little bit mathematical. That's why we're going to go faster for that. So the intuition is very simple. So how the trees are built in an automatic way, or how we can build the trees in an automatic way. The intuition is very simple. We take one feature, whatever it is, you know, days with fever, yeah? So, and what we're trying to do on our data set, we're trying to choose, we're saying that, okay, we need to, if you are with fever more than X days, and we don't know what the X is, there will be one way, and if you are smaller than X days, there will be another way. So, and how you determine that X, you're determining it by saying how we can maximize the information which we learn about the system by doing the cut. And for the people who are mathematically inclined in the audience, we are estimating the entropy, the change of the entropy as we're doing the cut. And we are just increasing the amount of information which we learn, and that's how we do the cuts. So when we're doing this process sequentially, so the choice is exactly dictated using some information concept, but essentially what you want to simplify your decision making on every step by using some information measures. And it's going to be now, I think it's going to be kind of a little bit formulated a little bit more formally. Yes, so we have a input data, which is, you know, we have n entries with the d features. Yeah, so we have a tree. So now we want to create a subtree, and now what do we want to do? We want to create a new split. So first of all, we can choose out of all features, we can choose the feature which give us the best information gain. So that could be the first thing. So you do the maximum information gain by doing first split, and afterwards you do the same game in each subnode, and you do it until you constructed the whole tree, or you reach the maximum number of leaves, because that you also can, sometimes you need to limit. Okay. So how we choose the best features? So, and the key idea is the simple and consistent explanation is the best, or it's also called Occam's razor. So essentially the feature which gives us the best and the maximum information. Okay. So in the example here is, so we have the data set which have people with the high blood pressure or without high blood pressure, and we have a lot of information. Yes, so kind of like high blood pressure, education, and is the person diabetic or not? And what do we want to do? We want to predict whether the person is diabetic or not. And we can choose, you know, if we do high blood pressure, so if the people have a high blood pressure or not, the diabetics will be with a high blood pressure like this, non-diabetics will be like that. And if we choose education as a column, 9th grade from 9th to 11 here, from high school grad here, some college here, some grad here. So, and the question is, which feature is more informative? So which feature can tell us more about whether the people are diabetic or not? Obviously, if the people have a high blood pressure and education, yeah? So that automatically implies so that if we have a subset with a high blood pressure and education, and we won't predict whether the person is diabetic or not, it's better to do first high blood pressure split. Yeah, and afterwards think, did the education give us anything or not on top of that data? Because if you don't have a high blood pressure, you're not diabetic, okay, we don't need to deal with you at all. The problem of classification is solved. And only if you have a high blood pressure, we can, at least in this data set, we can maybe look what the education is telling us. Okay? So, and in order to formalize that, as I mentioned to you, so in order to formalize it, we need to introduce some information measures, and let's take it carefully. Sorry. Okay, yes, and this will be a little bit mathematical, because what we need to talk about entropy, and we need to talk about the entropy of the data set before we do the split, and the entropy of the two data sets, the splits, after we have done the split. And that's what we need to compare, roughly speaking. And when we're talking about the entropy, we need to talk about this form of what is called the binary entropy. And with this definition, but essentially it's a probability of event on the log of the probability. It's a standard definition of the entropy, which is used like in Shannon, but also used in statistical physics. And it's a kind of like the measure of the information content. So what can we do? So what is the properties of that function, which is called entropy, is that, you know, when it's from 0 to 1, so the entropy and the probability, so if we have only two classes, it will behave like this. So if everybody is in class 0 or in class 1, or if the probability is 0 or 1, so if you have a maximum knowledge about something, your entropy is 0. And if you have probability 1/2, so it means that you don't have knowledge, because, you know, you have two events and the probability is 1/2, your entropy is maximum. Okay, so now we can, if we have everybody in the same class, the entropy is 0. And if we have the same numbers of the object from the two classes, the entropy is 1. Okay, so now we can do this game for our high blood pressure and education. So, and the question is, like, if we introduce the split, what will happen to the entropy? And based on that, we can estimate the information gain. And there is a little scary formula, but essentially what does it mean? It's a entropy before and entropy considering the split. Yeah. So it's an entropy. So when the value of the J is equal to nu and the probability that you get nu. So when we can formally calculate this formula, and, you know, this is called conditional entropy. And we can, for example, you know, look at the example of calculation. So we have 30 instances, 14 blue and 16 orange, and this is the split with 13 blue and 4 orange and 1 blue and 12 orange. So we can calculate the entropy of the original set, the entropies of within this split, and we can calculate the information gain. So, and if we get when we kind of, and what we want maximize the information gain, roughly speaking. Yes, so, and computationally, it's solved by maximizing the information gain. And I think here we're going to have a calculation what is happening in this case. And again, for those of you who are a little bit mathematically inclined, you can follow this logic, but let me just go quickly through. So we can calculate the entropy of the whole thing. And afterwards, we can now, if we split with the education, we can now calculate what will be with the high blood pressure, we get split like this. Yeah. So now what we can do, we can just calculate what is the probability if you have a high blood pressure, yes or no, and what will be the corresponding entropy of that subset. Or we can calculate the information gain, or we can, sorry, yeah, it should fit in, yeah. So, or we can calculate if we're splitting by education. Oops. Okay, so now we can calculate the information gain, and what we can see that the information gain, if we split with the high blood pressure, yes or no, is higher than the information gain if we split by education. So it means that if we want to build a tree, our first, for this particular data set, and the classification diabetic or not diabetic, we need to do the split first in the high blood pressure, and only afterwards we can split the education. So, and, you know, again, but from the practical perspective, scikit-learn will do it for you. Scikit-learn is just going to take, it's going to go through the whole features and evaluate it feature by feature, which feature will give you information gain and will build your decision tree. And even more, what scikit-learn can do, which is even more powerful, it can calculate to you, it's randomly, because if you have too many features, it might take a lot of time. But now you can take, if you randomly pick some features, calculate the information gains over there and build the trees based on subsets of features. And you get a tree. And afterwards, you do it again with some other random subset. And you get another tree, another tree, another tree, and you get many trees. And afterwards, what you do, you essentially average out over the results of this multiple trees prediction. And this is called random forests. And these are extremely powerful tools, which are relatively easy and fast to train. And I encourage you to use it if you cannot afford to train the large neural network models. So what do you need to avoid overfitting in the trees? Because you can build the tree till the end. Of course, you need more training data. This is always the answer. You want to remove the irrelevant attributes. If you can, you need to stop growing the tree when you're not getting too much information gain. So, you build the tree, you do the split, but on some stage, the information gain from the additional splits is too small. But it means that you need to stop. Enough. You don't need more trees. Or you can grow tree and afterwards cut some branches. And this is called post-prune, which also have shown to work nicely. Yes, you can play with the various tree parameters, tree depth, meaning how deep it is, splitting criterion, termination criterion, and pick the best performance. You can do cross-validation, and you should do cross-validation, or you can add extra complexity penalty for performance measures, and so on and so forth. Okay, so you can just, if you need to add more leaves, you can add, so that it will be a penalty, so that it makes more and more expensive to add more leaves, so that the algorithm will naturally stop in some balance between because obviously you can build the tree completely with all your data, but what you will get in that case, you will get overfitting. So you naturally need to stop somewhere. And that's how you avoid overfitting. Yes, so yes, stopping growth is a set maximum depth. So that we're going to see, yes, minimum number of samples in the node and so on. Okay, so let me so I think that we can probably go to the tutorial here because, okay, just very quickly. So what you can do, you can build, and the scikit-learn naturally can do it for us. It can build a collection of trees, or it's called ensembles of trees. And these are called random forests. And as I mentioned, it's extremely powerful approaches. What it essentially do, and there are different ways how we can build these ensembles. And generally, ensemble approaches are very powerful approaches, and the indication, or the idea behind the ensemble approaches, and there are different ensemble approaches, is very simple, that if you get, a models which can solve your problem, but the models are not very good. But if each of your sub-model, and you train many of them, but they give you, the probability of success above 50%. But if your models align, or are misinforming you on the different part of the data, in that case, if you're going to do just a majority vote, or there are some other more fancy ways of putting an ensemble together, what you can show, and it's shown mathematically, so that in the limit, you get a perfect classifier. So if you average enough so-called weak learners, so it means that the learner which have, the probability of success just above 50%, or probability of accuracy of classification just above 50%. But if you average enough of them, and if they align to you or misinforming you on the different parts of the data set, in that case, in the limit case, if you take enough of them, you can create something which is called the strong classifier or perfect classifier, which is going to do the 100% efficiency of classification, at least in theory. And this is very actively used, because I haven't seen too often people use a single decision tree, but the random forests are very typical. And how it's built in the scikit-learn, or in this example, is you take the data, you take the subsets of the data, and they could be overlapping, but the different subsets. You train decision trees separately, and afterwards you combine, and you can do different ways. So you can do the majority vote and several other approaches. Okay. Training and decision tree in a random forest. So we need to fix the number of trees, and afterwards we need to define what should be the depth of the tree, and we need to specify we're going to see how many parameters we are going to have. But even this, we don't need to do it directly, because scikit-learn will do it for us. And let's probably, yes, benefits of the random forest, that they're scale invariant, they are very easily trainable. Yes, and they're good in generalization. And there are not only the classifiers based on the random forest, there are also regressors. So you can also solve the continuous, you can solve the regression model. And also it's highly parallelizable because you can train each tree on a separate processor, meaning that you can do it independently, which is very important because if you need to train your machine learning model fast, you need to do it in a parallel way. So, and that is why, for example, as I mentioned to you before, the neural networks becomes extremely efficient before we learn how to train them very fast. In the search engines, random forests were used in the search engines because you can very fast train it. So you can very quickly update your model. Okay. So I think, let me see what's happening in the chat. And I think we need to go into okay, is the penalty function? Yes, the penalty function is something like a hyperparameter tuning, yes. Yes, how are we sure that we split into the test and training? How are we sure that after split into the train and test data, there is no mixed up afterwards? Because you control your code and you're not supposed to do a mix up, and you're supposed to do the training only on the training data and don't do the training on the test data. And that's how you make sure of it, because this is you as a person who is writing code supposed to control it. And that is why you're only supposed to use the test data in the very, very final stage. You can split your training data into the training data and validation data, do the cross validation and do all of that approaches. But when you think that you obtain the model, afterwards, you only that. You take the test data, you shove it in your model, you get predictions, and you estimate the accuracy, which you are going to report. Okay, so let me quickly. No, I think quickly afterwards we will get into the neural networks, but that I think I wanted to speak about tomorrow. Let me quickly upload the tutorials. Okay, it also speaks about a little bit ensembles, but okay, we can probably do it tomorrow. Just let's go into the into the examples. So let's first go into this item. And into this item, and yeah. Okay, so in Canvas, everybody should be able to see advanced regression example wine file and wine quality y.csv file. So let's go into that. Yes, I will upload later the correct the script with the things which I ask you to do. Okay, so what we're going to do, we're going to play a little bit with the random forest and also what is called lasso, and we are going to see what it is lasso and what does it mean. And so we need NumPy, pandas, which we have, scikit-learn, which I hope we already have, and seaborn, yeah? So what we're going to do, we're going to analyze the wine quality data set, which is essentially there is a whole bunch of characteristics of the wine and some quality of the wine, yeah? So and the characteristics of the wine are, I don't know, different acidities and so on. And this is the float. And afterwards we get, you know, the integer as the quality of the wine. So we can do the same as we've done in the previous case. We can do the pair plot. And we can see how stuff is correlated. But because we have more features, it's going to be a little bit more all over the place. But what we can definitely see that, you know, there are some features which are correlated in the sense that you see, you have something like this. Yes, so kind of like you increase one thing and another thing is increasing. And you get things which are looking like they're anti-correlated. Yes, so that you increase one thing and the other thing is going down. So which is already interesting, or features which doesn't seem to be correlated. Yes, because they're range here and the range here. So kind of like, you know, you move here and you don't move anyway on that axis. This is just a good and quick representation to you that, you know, yes, we have data and, you know, some features in the data are correlated. Some of them anti-correlated and some of them have nothing to do with each other. So this is a pretty typical situation. And okay, so we can also calculate the correlations formally using the heat map. And again, you know, as we've seen, you know, some features are correlated, you know, 0.62 is a nice correlation. Some of them anti-correlated, minus 0.76, the amount of the alcohol and amount of the density of the wine are anti-correlated. And we can check how it looks on the density. And where is, and the alcohol is here. Yeah, so you see, it's a little bit verticalish, but, you know, it's obviously anti-correlated in this way. Okay, so now we can do the split, test and training split. We can transform the data and the quality will go into the Y and the training, test and training is going to the X. Okay, so, and again, as you see, we're scaling data using the training data and the test data is just transformed. So as I mentioned to you, not to contaminate the training data with information about the test data. So we can do a standard linear regression, which we've done just now. Yeah, so we just create a model fit. And now we can print the mean squared error. Okay, or if mean squared error is not really telling us much, we can do R2, and R2 is, you see, quite low, which is not good. Yes, because it's, you know, it's good when it's closer to 1, and this is 0.25. Okay, so, but now what we can do compared to the previous notebook, because we also now normalized our features, what we can do, we can try to see that from the point of the linear regression, what is the importance of the features? Because that was the question, you know, and with the linear models, you know, we can very easily extract this table, and we're just saying that, okay, so the quality is anti-correlated, from the point of the linear model, which we know that it's not very good. Yeah, but within this linear model, it's anti-correlated with the density of wine, quite correlated with the residual sugar and so on. But you can see that, you know, to the question, oh, how can we understand which features are important and not important? First of all, we need to get a model which do a little bit better. But if we assume for a second that this model was doing all right, we could easily throw away these two features. Yeah, because, you know, their importance is quite low. And you can decide as the person who is designing the algorithm where you want to stop. What is enough? And you can design that, you know, more features are irrelevant, because this is also quite small value, so that you can decide that you want to throw it away. Okay, so let's try to do it a little bit better. And now we're going to do what is called lasso regression. And now the question is, what is the lasso regression and how we can find out? Who can tell me what is the lasso regression? Is there a magic bullet on identifying which random state is idea for any model? No, it doesn't matter. I mean, just forget about random state. Just choose it, fix it, and that's all. There is nothing special about the random state. So who's the lasso model and who's alpha? Okay, so that's better. L1 is lasso, L2 is rich. Yes, I think that is correct. Let's do scikit-learn. Lasso. So lasso is just your linear model, but with the loss function, which have L1 regularization. So we get a hyperparameter alpha. Okay, so what is lasso? Lasso is just linear model, but now with regularization. And here it's suggested to start with the alpha equal to 0,01. So we can do it, and we can check where we are. So we can get the coefficients, and we can get again the importance of coefficients. And you see, in the moment we introduce regularization, suddenly what we get, that, you know, again, alcohol, residual sugar is important quantities, and they become more important than density. And these three features are completely irrelevant, which is already very good, because, you know, regularization always helps. And you see, it's what regularization have done effectively. It's have made your model easier, because it's not just tell that these three features are not that important. They're just, okay, they're zero importance. Okay, so we can again estimate the error. We can estimate R2 score, and you see, kind of like in R2 we get a little bit better. Okay, so but now it would be nice to understand how bad or how good this lasso is if we do the cross-validation, which we haven't done in the previous case, yeah? And again, the beauty of the scikit-learn that a lot of these things are automatically included. So what we can do, we can create a sequence of different alphas, because, you know, this was, I mean, we just thumbsuck random alpha, and we get a better result. Yes, because it was 0,01. And now the question is, okay, can we do it in a little bit more systematic way? And to do it in a systematic way is exactly that. So we can create the array of alphas. You know, what this command is doing? It's creating us the sequence of alphas, but in the log space. Yes, because it's not very nice to have it, you know, because what you want kind of like, you don't want just 0,1, 0,2, 0,3, because you want it a little bit with scaling. And log is a good scaling, which can show you, okay, for the very small numbers, how it's behaving, and for very large numbers, how it's behaving. And one want to see it. So, and that's exactly what the log space will do. So if you want to see what it's do, it's just, you know, that will be your array of alphas, which is passing down. Now what we do, we do the lasso with the cross validation. We do it with the 5 folds, and we do the fit, and we see what's happening. Okay, the model is trained, and now what we'll get we'll get what is the best alpha, and the best alpha is this one. And using this alpha, what we can do, we can just predict everything. Okay, so we can get the coefficient, the importance of the coefficients, and we see that for that alpha, density is regaining the first spot, but the sugar, okay, the alcohol have lost its spot in the feature importance, and the citric acid is still irrelevant, but other quantities gain a little bit of relevance. But again, you can decide how many features you want to include and how many features you don't want to include. Let's calculate again. Okay, but now what we get, that on the training set where we've been doing training, that alpha performed better. Yeah, but the problem is that on the test set, it went down. So when you see, and that is the niceness of the using of the test set, which you really don't kind of like, if we would use it back into the training, we would contaminate the data. But it happens that, okay, on the training data set, this optimization over the alphas works nicely, but we see that in the test set, okay, it doesn't work that nice. What can we do? So we can try to play the game, and we can, for my question, who is lasso? Somebody responded that L1 is lasso, L2 is rich. One could try the rich regularization, which is L2, which is with the squares, and see, does it give you a better result or not? Because the language will be absolutely the same. It will be rich CV. So because, and that's again, that's the beauty of scikit-learn, because it's really the same structures which you can try and play around just to see what are you getting. But instead of that, let's try to play the game of random forest, and let's see how easy it is. We're not going to just build the decision tree. We're just going to build the ensemble of the decision trees. So, and it's also extremely simple. We say forest is random forest regressor. We make this forest out of the 50 trees, and you can increase the number of trees, but you should be careful to not make too many trees in your forest. Again, we fix in the random state, and we just saying, okay, fit, and it will fit for us, and we can see, how good or how bad are we doing. Okay. And after we've done that, we can also do not just forest predict, but we also can do we can calculate the cross-validation score. And we can also, we've done it for the mean squared error. We can also do it for the R2, but we can just by looking at the mean squared error, we can compare to what do we have. So training is quite low. I think it's even lower than we have, yes. Because training is, you see that the random forest in the training is giving you, almost of the order of magnitude decrease. On the cross-validation is not that good, and on the test data, it's decreased, but not as much. So it means that we are probably somewhere in a little bit, we are doing better than here, but still requires a little bit more playing around. And so kind of the playing around means that, we need to play with a number of estimators maybe, and with some other parameters, which were mentioned on the slide. So we need to decide how deep we wanted to go, because by default, kind of like when we don't specify any other parameters, if we just stick to what we have here, okay, so you see by default, if we didn't specify the number of trees, we would get a 100, but there is we can specify what is the max depth to prevent the overfitting. We can specify some other conditions, which we can, and we can see how it performs and whether it's performed better or if it's performed worse. Okay. So, and now what we can do, because again, we can specify these parameters, or we can do the systematic search within the parameter space. Yeah. So, and we can do what is called the grid search cross-validation. So, and what do we want to do? We want to say, okay, we want to see for the range of the max depth, which is from 10 to 25, yes? And we want to see max features from 6 to 12, which are included into each tree, okay? So when we say number of jobs is equal to -1, it means that we are going to use all available processors for doing the calculations. We fix in the random states, forest parameters to do optimization. It's going to look for all possible combinations of the max depth and the max features and see where we're going to get the best result for the 5-fold cross-validation. And be careful with running that, because these kind of searches can be a little bit time-consuming on your machine. Okay. Okay, so I'm done. Let's see what's happening. And yeah, it's fine, the same thing. So the max depth is optimal 21, max features is 6. And this is our negative mean squared error. So now we can do the estimates and see what we've got compared to cross-validation on test, compared to what we have before. It's a little bit improved. Yes, the cross-validation and mean squared error on the test are improved. So, and that is the example how to search for the optimal parameters. And yeah, we can check the R2 score. And as you see, the R2 is better than it was, because you remember we started from 0.25, 0.26, and now we're just above 1/2 on the test data, but it's still not perfect. And you know, that's the game of the machine learning. Now you need to play with the parameters or with the hyperparameters to try to bring, you know, to get the R2 score higher. And in that case, you hope that, you know, your model will have a good enough generalization ability. So what else do we have here? So we can check, you know, which other metrics you wanted to use. So because that's all sorts of different metrics which we have here. And no, what we can also do, which is feature importance, we can do the same thing as it was happening with linear models. And random forest is telling us that the alcohol is a crucial feature in the wine, which is a little bit disappointing, but okay. But again, this citric acid and these acidities, as it was with the linear models, they were taking the back seat, and they still keep in the back seat also here. Okay. So, and the question is, this natural question is like, oh, you know, we just run optimization in the parameter space. Yeah, and the question is, okay, so what's next? So we can have a higher or kind of a bigger search space. But the problem with the bigger search space, because already here we have 240 or 50 fits. And, you know, we're adding more items to the combinations. It will going to take longer and longer and longer and longer. And the question is how one can do it. And the answer is, traditionally, you can just take not everything, you can just take it randomly. And we can do it randomly. So when we can do a randomized search, and you know, we can say that, okay, we don't know how many estimators we need, and we want to look from the very shallow trees, 10 estimators to 1,000 estimators with a step of 40. We can again look on the range of the max depth and the range of the max features, and we can just run our randomized search. I hope it doesn't kill my machine. Okay. Oh, and we can get what are the best parameters we got. So we get the number of estimators. Okay. Feature 6, depth 21 is consistent with what we have before, which is a good sign. So it means that it's probably something correct. But we see that the number of estimators is, instead of 50, it's better to be 130. So we can estimate mean squared error, which I think is getting better, 366,398. And what do we have here? No, 366 is it's the same, so it doesn't improve much. And what's happening to the R2 score? Okay, let's also recalculate it. It's marginally improved, yes, because that was 0.5. Ah, no, it's the same. It's absolutely boring.
Prof,
Yes.
it's tea time now.
Okay, I think we are almost finished. Okay, we can have a tea time and we can finish after the tea time.
Thank you. Hi, Prof. Yes, you can continue.
Okay. So let me share my screen. So, oops. So, okay, so what we've seen is this one. Yes, essentially, so that it wasn't really impressive, the results, but we can still estimate the feature importance, and we can get which features are important. And we see that again, the alcohol becomes more important feature and so on. So, and by the numerical values, we can estimate it, and we can take a decision whether we want, which features we want to keep in our analysis and which don't. However, it's still not very impressive performance. And what we can do, we can try to plot the same graph and realize the mistake which we've done and why the performance is not very impressive. Yeah, so this is the actual wine quality, and this is a predicted wine quality. And what is our problem? Based on this figure. Sorry? No, there is a relation because this is actual wine quality in the data set vs the wine quality which we're predicting. What is the obvious problem? The obvious problem that we're solving the wrong problem. Because we're trying to predict wine quality, which is a numerical quantity. Yes, kind of like which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're trying to solve the regression problem. And we see that, this is an example that you can use a regression to predict discrete values. But the much better approach in this particular case, no, it's not a multiple predicted values, but because, because we're solving classification, but using the regression. So it might work, and it's partially working, but it's not giving the nicest possible results. So your little task for tonight is do the same game, but with the classifiers. And essentially it's boiling down to replacing in the random forests the regressor by classifier, and it will work. Okay, so, and now let me see what's happening in Canvas. No, it's not in Canvas. So let me add one more file to Canvas where we can try to solve classification problems. Oops, stop sharing for a second. Okay. Oops. And now you all should see in the Canvas one more file, support vector machine classification. And let me. Okay. So, and we're going to do it not for the wine. You're welcome to do it for the wine by yourself, but we're going to do it for the medical data. So, and we're going to deal with a rather standard and famous data set. Again, we need the standard modules which you all have: Pandas, NumPy, Matplotlib, Seaborn. So scikit-learn have a series of the data set, and this is a standard cancer data set. It's have a set of keys. Standard, we can read the description so that we can get, how many items in data set and so on and so forth. It's a curated data set. And as I mentioned, it's quite famous, or one of few quite famous data sets. So we have a sequence of features. Yes, so we can go through the feature names, which are different characteristics of the tumor. And we can also check, to check that, they all have non-zero values. We could see it directly, but we also can do it programmatically, yes. So we can have, if there is a non-zero value, that would be the Boolean variable true or false. And if it's true, it will be transformed under the sum into the 1. And if it's false, it will be transformed under the sum into the 0. Yeah. So in NumPy sum of that will give us 0. If there is all the values are filled up, and we see that all the values are filled up. Okay, so we can check what is the target variable, and it's 0, 1. So cancer, no cancer. Yeah, so there is other features. Yeah, and now what we can do a little bit of EDA. So we can now plot the distribution of the values as a function of is it cancerous or non-cancerous tumor. So first we can count the number of entries for the cancer and non-cancer, and we see that we're dealing with a little bit unbalanced data set. Yeah, so we have roughly 220 or something like that entries of what kind, and 350 entries of the other kind. We can look for distribution of values using the box plots of the features for the cancerous and non-cancerous case. There is some bunch of warnings which you can ignore. And we get the distributions. Yes, for example, cancer, no cancer, and we get the box plots. And what is the meaning of the box plots? What is the middle part of the box plot? What is the width? What is the tails? And what is the dots outside? Sorry? Okay, so center is, sorry? Median, okay, median, good. So the blue one or the green one, the width of this is? Good. And the tails? Okay, center is median, outliers are dots, yes. Okay, so yeah, somebody's writing minimum Q1, median, Q2, max, yeah. Okay, good. Because in some fields, people don't use it and they don't know it, and that could be surprising for the people in some fields. Okay, so we can see, how data for the cancerous and non-cancerous cases are distributed. So we have all our features, and we can also check that the features are not linearly separable. So yes, because you see kind of like cancerous, non-cancerous, for some features, we can see that they're obviously overlapping. So we need to do some, machine learning, which is kind of a little bit non-linear. Okay, so we do again standard test train split. So we get data frame for our total data and the prediction, target. Okay, so again, train test split 30%, and you see in this code it's a random state 101, because it really doesn't matter as long as it's just fixed. Okay, so and now again, as I mentioned to you, it's absolutely the same. What you need to know the list of models and what they can do and what are their hyperparameters, but the language is afterwards the same. So we just take the support vector classifier. You remember that, the dots, and we need to draw the plane, and we need to push the plane as further away from each other. We just do fit. And afterwards we do predict. We can plot not just accuracy, but the confusion metrics. And because we've seen that we're dealing with the unbalanced data set, so the confusion matrix is better. So what we see is that, the true positive 56, true negative 1 or 10, false positive and the false negatives are 10 and 3. Yep. So good. And based on that, we can calculate all sorts of medical characteristics for this kind of model. We can calculate sensitivity, we can calculate specificity, and so on. Yeah, but now we can say, okay, how can we optimize these confusion metrics? How we can make it better? So what we can do again the grid search. So we can, and in order to understand what grid search are we doing, among the which parameters, we just need to go into the documentations about the support vector classifier and see which parameters are there. So there is a parameter C, there is a parameter gamma, but this parameter gamma is only for these types of kernels, which are called radial-based functions. But okay, for us, it doesn't matter. It's just, it's just a way to measure measure distance in some space. And it's have a in front parameter gamma, and the C is some other coefficient. And when we don't specify it here, we use by default some values, and we can check. Scikit-learn, C, support vector classifier. Yeah, so that C was 1 when we don't specify it. By default, it's also using these radial-based functions. And gamma coefficient, and we see that there are some bunch of default values. And you see kernel, it could be linear kernel. In that case, support vector classifier is identical to just a linear model, which is used for the classification. But the kernel could be polynomial. It could be radial-based function. It could be sigmoid, or, which is the kind of the interesting bit, it could be precomputed. And one is using the precomputed kernel if it's coming from some interesting device. For example, some of my students are using precomputed kernel because they're precomputing it on the quantum computer. And in that case, it's called quantum support vector machine. Okay. So, and again, if we use a polynomial kernel, it will have by default the degree 3, or it could have some other degree if you specify it. Okay, so now we can just play with the parameters and see what are we getting. So that was our confusion matrix. Now we can do the range of the C's, do the range of the gammas, and the gammas, as I mentioned, only the part of radial-based function. Okay. So now we will run the search, and be careful with running search because it could be expensive, but okay, it seems to be fine. Now we need to do the fitting. Okay. And we need to extract the best parameters, and best parameters, according to this little grid search, are looking like this. C is 1 as it was, gamma is 0,001, and we're still staying with the same kernels. We can do the prediction, and we can construct the confusion matrix. Okay, so confusion matrix is now 59, 101, 74. Okay, so it's improved, this decreased. So, but the problem is that, okay, at least the off-diagonal elements, this a little bit increased, but this decreased more. So we can claim that, the confusion matrix improved, but, one need, in principle, calculate all of this precision, recall, sensitivity, specificity, and see how it's behaving. You can change the range of parameters of the search. You can do the search again. And you see, this is the thing is like, You take one range, you see the result. You take another range, you see the results, and you decide, and you do it in an iterative way, and you can obtain nice results. Okay, and we get that, it's roughly the same. This confusion matrix is exactly the same as this one. So our another search which identified different parameters, yes, because C is 100, gamma is 10 to the minus 5, was not much better than C is 1, and gamma is 10 to the minus 4, by whatever reason. So, and one can just play this game and predict. So, and I suggest that you can try to use the support vector classifier to do the wine classification, but in that case it should be multi-class classification, and of course the random forest classifier to do the same, to do the wine classification. And let's see for the questions. What is so grid search is just it's just a brute force search. Grid search is just a simple brute force search. So we take the values of C 0,1, 1, 10, 100,000, gamma 1, 0,1, blah blah blah. So you take the couple of these values, evaluate the performance of the model. Next couple of values, and you take all the pairs or modern pairs. If we would have here not just radial-based function kernel, but if we will have a multiple kernels, you just do it couple by couple, and that's all. There is no deep insight in that. It's just it's just a brute force search, and that's why in the cases like this we can do it, but in the general cases it's just computationally unaffordable. Okay. Any other questions, guys? Mm-hmm. Mm-hmm. No, but I mean, okay, so when you do the grid search with cross-validation, you don't need to do cross-validation on top because it's already doing it. You might want to do cross-validation after you find the optimal parameters with the following idea. So because when you report the when you report the performance of the model, we say accuracy is 80%, yes, 0,8. But as any numerical experiment, it's supposed to have precision. It could not be a number. So in that case, what you will do is a cross-validation. You're going to do cross-validation, but you're not going to pick up, the best of things, but you're just going to get the range of the performances, you do, for example, threefold cross-validation. So you take this bit as the validation, this is as a training, so you get performance. You do it 3 times with the different bits, you get 3 different accuracies. And if you do things right, they wouldn't be different too much. But what you will get from there, you get the statistics, you can calculate average, and you can calculate a deviation. And you can report it now as the proper physical result. I don't know, 0,8 or 0,79 plus minus 0,02. Because you're supposed to have error bars always. Sorry? Yes. Mm-hmm. So, but R2 cross-validations mean that it just calculates you average of over the several cross-validation. Yes, it just give you the average.
Can you use the grid search in the case of the L2 perspective? Or do you have to use both in the same?
No, you need to. Okay, so why do you use grid search? With cross-validation or without cross-validation? You use the grid search to find the optimal hyperparameters. And afterwards, so one thing is that you need to find the optimal parameters, and afterwards, you need to report your results. Yes. So, and for that, you need to do the cross-validation. But when you do the grid search cross-validation, you just make sure that, you know, your hyperparameter search is better. Okay, so can we get the slides? Yes. Would you suggest the random forest using? Would you suggest the random forest using 15, 20 years of hourly time series data for the time series forecasting? You can try, but you know, to do the time series forecasting, even without neural networks, there are other well-working methods, and it also depends. And you know, there was some experiments I've seen that, you know, with some time series data, and I don't know, with some neural networks, but essentially the outcome of that was that essentially what even, you know, fancy neural networks do, they will do some very glorified version of the Fourier analysis with the time series data. So if you really want to do some kind of like, if you want to get more than the Fourier from time series data, you need to kind of supply it with extra information. And the same thing with, you know, if you just supply the time series data, whatever your algorithm do, it's going to do, you know, very likely some form of, you know, glorified Fourier. So I would just time series, I wouldn't really do kind of like, you know, for the time series, there are, you know, standard time series statistical approaches which are working very well. So like ARIMA, SARIMA, and, you know, the modern versions of them. For example, Facebook have I think it's called Facebook Prophet, which is essentially some very fancy nonlinear time series regression tool, which works very well if the only data is the time series. If you supply some other data to the mix, you know, I think some other things could be useful, but I don't know. Sorry, then is breadth first search algorithm used in a grid search to find the optimal parameters? I don't know. Not sure if I missed this, but do you have any book recommendation for getting into the machine learning? There are too many books to recommend. And I don't know what I can. There are some standard books, and it also depends on what kind of machine learning you're talking about. If you're talking about the deep learning and neural networks, there is a standard book by Benjo. It's called Deep Learning, and they have a free online version. Deep learning. No, not Daba, sorry. Deep learning book. That's so there is a print version of this book, Goodfellow, Benjo, and Corvell, but this is kind of online free version of this book, and this is like a standard book on the deep learning. So if you want to learn everything about neural networks, one can start here, and this will be, you know, a very good book. To learn, you know, these classical methods of machine learning, I don't even know. No, I mean, it's all. No, I'm looking for particular. No. No, there is a classical book. I see the front of the book in my head, but I don't. I can check and maybe I can check and maybe say tomorrow. But you know, there are some, you know, standard books. Of course, you know, what you see by default choice is all the kind of the modern books, which are good, but which are usually more on the kind of the experimental or numerical experimental aspects. But there are some standard books which, you know, kind of like which explain the fundamental things, and that I can say tomorrow. Okay, yeah. Yes, the fundamental things. Yes, I agree that, you know, the NG course is also, yes, is a very nice example of the standard fundamental course on the machine learning. Okay. So, yeah, I mean, these hands-on books, some of them are nice, some of them are not very nice, but at least you can learn, you know, how to write the simple algorithms using those books. Because I think this was one of those which were directly seen in the. Yeah, but again, just keep in mind that there are so many resources about machine learning. So there are much more resources about machine learning probably than any other subject in the modern hot topics, so to say. So from this perspective, there is, you know, there are wonderful courses in the YouTube. There are courses, there are books, and a lot of those books are free books. So there is literally no excuse not to learn it. Okay, so should we wrap it up for today?